Good morning, everyone. Colleagues, ladies and gentlemen, a warm welcome to the Royal Academy of Sciences and to our Bayer Hall. Bayer Lecture Hall is renovated recently, and I'm very happy to be able to use it for this event. I'm Ellen Mons, General Secretary of the Academy since the 1st of January, and I'm delighted to be able to meet all of you here at the Academy. Academy is an independent institution, founded 1739, almost 300 years ago, and whose overall objective is to promote the sciences and to strengthen their influence in society. In these times of conflicts, wars, energy crisis, and disinformation, the opportunity to gather scientists is maybe more important than ever. And meetings like this one facilitate this continued dialogue and scientific discussions that advance science and fact-based knowledge. It's therefore a true pleasure to host so many brilliant scientists in the field of emerging optoelectronics here at the Academy today for 2 days. And thank you for making the time to come, to travel all the way to Stockholm. And the competition is strong with the MRS spring meeting in Honolulu. So thank you very much for coming here in this cold weather. Our events team, Peter and Veronica and Pierre, they have worked hard in the planning of this event and to make this possible and make your days as comfortable as possible. And if there are any practical questions, Peter is at the back there, and he will be with us all the time, and you can reach out to Peter or Veronica. Last but not least, I want to thank Uling and S for taking the initiative, and Feng for preparing the program, assisted by Tony, Ule, and me. And thank you very much for making this possible. Before I give the word to Feng to introduce the conference, just a few practical things. This hall has microphones in the roof. So therefore, we will not hand out microphones when you have questions. That's just handled by this very nice room. But it also means that every small sound that you make or whisper or, secret things, it will be heard. And since we are recording the lectures, for those who has accepted the recording, it will be heard on the recording. So think about it, it's something that can be disturbing. The recording can also be edited afterwards, I heard from Peter, so we can deal with that. So with this, I would like to give the word to Feng to introduce the conference.
Yeah, thank you very much, Ellen. So my name is Feng, professor from Linköping University. One more time, I really appreciate all of the speakers who travel long way from all over the world to Stockholm. For this 2-day event, and also all of the participants all over Sweden. And I see from the participant list, I also see some participants from abroad. I really appreciate that. So I think most of the Swedish researchers working on emerging optoelectronics, organics, perovskites, with some representative in this room. So I really thank you all for coming. And I would also thank the sponsors which generously supported this event for the Academy in the framework of KVA Symposium and Marcus Wallenberg Foundation for International Collaboration in the frame of Wallenberg Symposium, and also Tega Alanda Prize, and also Nobel committees for financially supporting this event. And I really look forward to the 2-day program. Very line of top speakers, and also during the fika and lunchtime we also have posters outside from researchers in Sweden. So really look forward to all of the discussions and program. Thank you very much. And with that, I would like to welcome Köhler to share the morning session.
almost on time to start the first session. My name is Olle Inganes. I'm a member of the committee. I've been active in this research community during my life in science. I'm now emeritus professor. And I'm very happy to introduce as our first speaker, Richard Friend from Cambridge. We'll talk about spin radical molecular semiconductors. There's no way I could easily introduce Richard. I can only say he's the doyen of organic electronics. That's the man. Richard, the floor is yours.
Ellen, Feng, Ole, thank you very much for your remarks. It is a real pleasure to be here. Coming a bit further north at this time of year is always a complete treat. It's, the sunlight is very uplifting. And in many ways, a lot of today is going to be about light. Light is good. We need it all the time. So the field of thin film molecular electronics goes back to, in terms of usefully working devices, to the late 1980s. And I have to say, back then, it did seem we were playing. We made devices that lasted for a few hours. They weren't particularly bright, but it was just interesting. I think what has been so surprising is that a few decades later, we turned out to have got a very consequential technology. And that, at the moment, is the organic light-emitting diode. And everyone in this room, of course, possesses several million organic light-emitting diodes because they are the ubiquitous display technology for smartphones and increasingly for displays of all sorts. I don't need to enumerate their virtues, but they're bright, they do color very well, they're thin, and they're power efficient. So those are compelling reasons for industry to adopt them. But it's all a big surprise, and in some ways there are still quite a few surprises. What are the things that have turned out to matter? Well, one element is that although molecular materials, pi-conjugated molecules, have been known to be luminescent for forever, they're used as dyes in laser dyes, whatever, bringing them into a solid state can cause problems, and engineering materials so they remain bright in a semiconductor context has proved to be more successful than I think we expected back in the 1980s. The second point on my list here is that in spite of the fact that we don't think of organic materials as particularly stable, they are electrochemically stable. It is possible to reversibly oxidize or reduce to form charge transfer complexes. We do that when we dope surface layers to be able to get good charge injection or extraction in LEDs and in solar cells. But the electrochemistry tends to stop there. We have materials where we don't do disruptive breaking of covalent bonds. So if you look at failure mechanisms in OLEDs, it tends not to be at the interfaces. There are some problems with highly excited states formed by bimolecular collisions of excitons, but the basic electrochemical stability has been exceptional. And of course, we tend to use molecular layers pretty frequently in Perovskites because they are quite good at not being destroyed by moving ions. There's been wonderful work going back to the original results from Ching Tang at Kodak on heterostructures that have been critical in making it possible to control where carriers emanate from or move to. And that again relies on the remarkable stability of heterostructure molecular materials. The focus for my talk is spin. Spin management is a big issue. It matters a lot for OLEDs, where the triplet problem is part solved, but not completely. And of course, as we now understand better, a good solar cell ought to be very luminescent when it's not extracting electricity. So we worry about luminescence yield there. For those who haven't been exposed to any of my talks before, this is an excuse to show a little video that I always have shown before. It's a video made back in about 20 years ago. This is the work of part of the Cambridge group. Every one of the names there is a full professor somewhere. Singapore, Heidelberg, and Cambridge. But back then they were more junior. But what we have here is a large transistor with interdigitated gold source and drain electrodes. You can see the pattern on the right-hand side, with a channel length of 20 microns, so it's easy enough to see. The device structure, I will, I'm not sure whether I'm very good at getting this to work. So the device structure, it's a solution process structure. We have a glass substrate. We've evaporated gold source and drain electrodes. We've spin coated a green layer of polymer. Its chemical structure is on the bottom here. It's a pi conjugated polymer which emits green light. We've spin coated a layer of dielectric with a different solvent. It's polymethyl methacrylate. And then we have a semi-transparent layer of gold as a gate. And it turns out we can either P or N drive this device, or if we put a large source drain voltage on and a gate voltage somewhere in the middle, we can simultaneously arrange for, I'm not doing very well with this pointer, okay, okay, oh, there it is, okay. Negative charge accumulation on the left, right charge accumulation, polar charge accumulation on the right. So the little video, which I'm now going to play, is where we're adjusting the gate voltage to choose where electrons and holes meet as they're dragged across the channel. They're emerging under one of the electrodes, and then they will, the line of accumulation of light emission sweeps across the channel. You can see the fringe electric field lines around the edges, and then the video dies in a sort of whimper as the recombination line disappears under the far electrode. So I show that partly because it's never proved to be useful, but it's a nice video. But really it illustrates most of the key attributes that demonstrate that molecular systems can make good semiconductor devices. We've clearly been able to get a field effect. We can move electrons, we can move holes. You can see them being swept 20 microns, and where they meet, we get light out. So that looks like something useful. Well, back to what I mentioned earlier, and that is the triplet problem. So the problem is that molecular semiconductors in general, but increasingly not always, have relatively confined molecular excited states, excitons. So an electron-hole recombination process, or absorbing a photon, tends to produce a bound molecular excited state, or exciton. And because it's bound, it's a Coulomb energy that is responsible for that. There's a large exchange energy, because that's also a Coulomb integral. So there is a lower lying triplet, and that might give phosphorescence. And if we photoexcite, we wouldn't see many of them. So the excitation across the, completely failed to make this work. Okay. So excitation within from S0 to S1 will produce singlets which will happily decay. But if we form triplets, then of course they're less likely to decay. And the problem with the organic LED is that we bring together electrons and holes with no spin, overall spin state predetermined. So statistically, 3/4 of the recombining electron and holes form triplets, and they wouldn't emit. I've managed to lose something on the slide here, but I think it's a Mac conversion problem. Okay, so what we have with triplets, we would lose emission. What we use to get emission for in commercial LEDs, for red and green, the triplet state is made phosphorescent by adding a heavy metal such as iridium or platinum. But in today's cell phones, the blue pixel is still relatively inefficient, and in fact most of the emission comes from singlet emission, but with some capture of triplets through triplet collisions that can fuse to form singlets. We're going to hear in the next talk about materials, TADF materials, where the exchange energy has been reduced so that inter-system crossing back to the singlet is possible, but it is still a significant engineering challenge. If we look at organic solar cells, which now are pretty good, we have power conversion efficiencies of up to 20%. 20% used to be a good number, but it's not high enough these days. How are they made? Well, they're made in a very crude imitation of nature, where the large exciton binding energy is overcome by forming heterojunctions between donors and acceptors, where the lowest excited state involves a charge transfer from donor to acceptor, but that requires a large surface area so that wherever a photon is absorbed, the exciton has a good chance of finding an interface. So the field has been very successful in various ways in making bulk heterojunctions, intermixed materials acting as donor and acceptor, and that has worked very well, and that's how we've managed to get to 20% with some of the organics. I show on the left the foundational paper from Qin Tang back in 1986. The problem now is we need to get past 20% to be useful, and we run into the problem that triplets do matter. It's a topic that's bothered us for quite a while. Our most recent paper on the subject 5 years ago, Alex Gillett's paper, we were able to count quantitatively the formation of spin triplet excitons through recombination of photogenerated charges, and those triplets they look like loss sources, and it's those that are one of the factors that limits efficiency to 20%. We need to find ways to avoid those triplets. So that brings me on to the title of my talk, which is Spin Radical Systems. And the proposition is that if we can change the electron count and therefore the spin count, a lot of the energy level structures get rearranged in a way that can be quite helpful. So organic radicals, most of the time we think of these as extremely bad for health and things to be avoided because they're chemically reactive. But there are quite a few based on pi conjugated materials where they're not intrinsically any more problematic than the closed shell systems we usually use. And the key is that the potential for reduction, which would mean putting a second electron onto the radical, or oxidation, removing the electron from the radical, if those two energies lie within the ordinary operating window that we use for electron and hole injection extraction processes, we're not really in a very different place to using closed shell systems. So this radical, TTM, has been around for a very long time. The radical is there as the black dot at the center of the molecule, where we have 3 carbons. It's made by, first as a molecule with a hydrogen in place of what becomes the radical spin, which is abstracted chemically at the final stage. There's a huge literature on radicals, most of it to do with their electrochemistry. They are potentially quite useful battery electrode materials because the redox is quite straightforward, but they can be bright. Most of them are not. There was a very important paper from a group in Barcelona back in 2006 reporting that the attachment of a carbazole onto this TTM radical produced a relatively efficient red near-infrared emitting material. So this is one that we've worked with a lot, where the effect of adding the carbazole is to change the electronic excited state, which becomes a transition that takes an electron from the lone pair on the nitrogen onto the vacant space level on the carbon radical, and that transition is quite strongly optically allowed, and gives rise to quite bright emission. So in our lab, Feng from Jilin University came as a visitor for a couple of years, working with Emrys Evans, then a postdoc in my group, and we managed to make some relatively efficient light-emitting diodes with this material. And what they demonstrated is that we didn't have a triplet problem. So if I take you to the right-hand panel, this material emits in the near-infrared just beyond 700 nanometers. In the right conditions, we had very high photoluminescence quantum yield, which is why we were able to make pretty efficient LEDs. So let me take you to the center panel. The HOMO here is the HOMO associated with the carbazole, so it's the, in this case, it's the nitrogen lone pair. The lowest unoccupied level is already singly occupied, and that is associated with the radical. And photoexcitation up and then down is what we see if we just photoexcite or electrically excite, because the next highest spin state, or the next available spin state, is the quartet. And in this simple scheme, the quartet must involve occupation of the LUMO as well. And there are one or two tricks here, but very obviously, it's not going to be a lower energy state, it's a higher energy state. So simply changing the electron count, the lowest energy excited state is now emissive, and we don't have a problem with that we have with closed shell systems, where we have to worry about the triplet. It is surprising to get organic materials that are efficient emitters in the deep red and the near infrared. If you go through the catalogues trying to find dyes to do staining of biological tissue or laser dyes, the infrared ones have terrible luminescence yields. The problem in general is that because organics have quite high vibrational frequencies, it doesn't take many vibrational quanta to span the electronic gap, and that then causes quite efficient quenching. And the culprit for many of our materials is this ring stretch from aromatic to colloidal conformation, 1600 wave numbers. We regularly see that as a vibronic sideband in luminescence. But it turns out that by luck, we had stumbled across materials which can avoid this problem. So here are two very similar molecules, which have on the left a very poor luminescence yield and quite a fast luminescence decay, and on the right a very high luminescence yield and an obviously much slower luminescence decay because the non-radiative component is reduced. The difference is in the connection point onto the carbazole, and on the left we have the lowest excited state, HOMO level, is actually a pi state. We have para-coupled 3 phenols that have pulled the pi HOMO level to be the lowest pi state. The lowest, the pi state is the lowest HOMO. On the right, it's the nitrogen non-bonding. So what we have on the right is an optical transition from non-bonding to non-bonding. And non-bonding, particularly for the carbon, means insulation or decoupling from vibrational modes. The non-bonding level by symmetry is non-bonding, so it's not affected by local geometry, it just stays there. And we think that's how we've managed to decouple vibrations and keep luminescence yields up. There's quite a lot more detail in Pratyush's paper. There's another element which is probably very relevant for TADFs, and that is that if the excited state has charge transfer character, where in our case the electron is on the radical carbon, the hole is centered around the donor nitrogen, the phonons, the local vibrations, turn out to be, as Pratyush has modeled, very localized. So if you want vibrational coupling, this Zen problem of the sound of one hand clapping, you need to couple both electron and hole, but if the vibrations only sit on the donor or the acceptor, that again helps cut out the vibrational coupling. So it's been a bit of a surprise. I don't think this is the last word, but these are remarkably luminescent. So we have made LEDs from these. These are some of our more recent results. The scheme on the left, the colorful set of blocks, is to illustrate the sort of structures that are used in today's organic LEDs made by vacuum sublimation, a series of layers of organic semiconductors, mainly bought from off catalogues because they're quite widely available now, where the bottom of the colourful bar is the HOMO position, so that's the oxidation potential, the top is the electron affinity. And what is done is to cascade holes from the left and electrons from the right into the to the light emitting layer. In this case, it's we've co-sublimed MADN, which is an anthracene derivative, with our TTM. Here it's with a triphenylamine, which makes it even redder than the carbazole. It's a 3% of the light-emitting TTM in the MADN host. And we managed to get what we think is the record for the thin film infrared-emitting LED. We've now more recently pushed what we reported 10%. We've now got 13% external quantum yield, which would require a luminescence yield of about 40%, which is what we measure. And that's assuming that we have all electron-hole recombination events produce potentially emissive excitons. So that works pretty well. Now, along the way, what we, of course, were doing was optimizing what the host would do. That's the MADN, the anthracene derivative, because it clearly has a wider gap than our emitter, and we don't want that wider gap to cause too much trapping of electrons and holes, because it makes it hard to haul electrons and holes through to find the emitter. So we can reduce the gap of the MADN, or whatever we choose to use, so far, until something changes. And the thing that changes is when the triplet level in the host hits the doublet level in our radical. Because we have spin, spin into conversion is very easy. And actually, by the time we get to MADN, its triplet energy is about the same as the doublet energy on the TTM. And as reported in our paper, what we see is actually the luminescence is stretched out. It's out to a microsecond rather than 10 nanoseconds, because there's a dynamic equilibrium between doublet exciton and triplet exciton. And the really unexpected news is that usually if you start mixing things with spin around, things go wrong. Here, they remain bright. It doesn't introduce a quenching channel. So that appreciation that we could perhaps access higher spin states has pitched our research, I have to say, away from energy solutions, but more to spinny things. But the common theme is we're working with materials that are bright, and engineering materials to stay bright opens up so many opportunities. So the first example is where we covalently attach our doublet on the left to something that can support an excited state triplet. These are the molecules, again, due to Feng. I should mention my then student Sebastian Gorgon, who did a huge amount of this work. So on the left is a material similar to those that I've shown you, where we have a doublet, because we have one spin. On the right, we have the same thing with an anthracene attached to it. The anthracene, of course, is a blue luminescent material with a wide gap, but its triplet energy is about 1.8 electron volt. It's basically the same as our TTM. So we have an energy degeneracy, or near degeneracy, for those two possible excited states. And when you photoexcite, what you do is generate more or less quantitatively a quartet. we end up with a coupled spin system of the triplet on the anthracene with the spin on the radical. So there's an EPR spectrum for those who like them on the left, but it's broad and complex and clearly indicates that we've got a surprising spin object. But the key is that it's still optically accessible. It can't itself emit. It is, if you like, the triplet, the equivalent to the triplet. But the exchange energy is small, and we can make it, and Sebastian showed how we can manipulate the overall spin state, and then it will reverse instant cross and re-emit. The line shape actually swaps sign between 1 and 9 microseconds. As we form it, we preferentially populate the plus and minus half levels of the quartet. Those are the blue, big blue blobs on the left. At later times, when we start to reverse instant cross, again we take the plus and minus half levels back to the doublet, leaving behind an overpopulation of the plus and minus 3 halves levels, and that's what causes the swapping over of the sign of the EPR response. So it's a well-behaving structure. More recent materials, we have a luminescence yield of 40% or more, which is pretty useful. So that was example number 1. Example number 2, which is our ongoing work, is where we've just coupled radicals together. I've optimistically suggested we have an infinite chain, which I'm not going to talk about, but we've gone somewhere in that direction. Here, I hope this isn't too much of a conceit, but a string of radicals with some electronic coupling is a Mott-Hubbard system to those who come from that world of physics. I used to listen to Neville Mott talking about it when I was a research student in Cambridge. It is the metal insulator problem. If I take a string of objects that have a net spin, and classic examples are materials like nickel oxide, and I couple them together in a solid, why isn't it a metal? Why don't the d electrons form a band, and just on band filling arguments we should have a metal? Well, the answer is because the Coulomb repulsion is large. It's too expensive to move an electron from one site to the next, because band transport means that we move carriers around. So the standard Mott-Hubbard description of that system is that its ground state is an antiferromagnet, and the reason for that is that in perturbation theory, the first term you would put in beyond the ground state would be a state where we've moved an electron from one site to an adjacent site, only possible in a singlet configuration. In that community, this is sometimes called a hole-on, double-on, but it costs energy, and the energy, very crudely, is the on-site Coulomb energy, the Hubbard U. And that, as a ground state, is where most of the high-temperature superconductors are before they're doped, and they are Mott-Hubbard insulators. The exchange energy is something like T squared over U, where T is a interspecies coupling, and U is that on-site Hubbard energy. Our input on this is that transition, that excited state, is actually radiatively coupled. You can certainly see emission from that state, if not absorption. It's slightly puzzling because the two levels have exactly the same wave functions, but there's a large dipole as you move charges between the two, and it's something that Mulliken had sorted out in 1950 in the chemistry community. So the charge transfer state is accessible. So I'm going to give you a first example, which is, I wouldn't say particularly useful yet, but it's a thought about making an organic solar cell without requiring a heterojunction. So we're starting with some radicals. The molecules here look similar to those that you've seen, so the TTM motif keeps being used. We have phenyl side groups. These are due to Petri Merto and Hugo Bronstein in our chemistry department. The phenyl groups at the end provide a little bit of extra intermolecular coupling when we put these together. We have, if we bring two molecules together or bring them into contact and they happen to be in a singlet configuration, there's a possibility when we photoexcite that we first go up to a pi star level from the non-bonding level, but there's then a charge transfer to form a hole on the left and an electron on the right. The overall cost for forming that charge transfer is the Hubbard U. If that Hubbard U is less than the energy from non-bonding up to pi star, it's the lowest energy excited state. I can see some puzzled faces. We puzzled a lot about this. Let me try and convince you. On the right, here is some electrochemistry showing the change in absorption, starting in yellow with the straight molecule. In red is where we've reduced with a peak in absorption near 600, and in blue where we've oxidized with a peak out towards 800. That's just standard electrochemistry measuring the absorption spectrum as we go through the different redox states. So we've now got a film, about 5% of our radical in an inner molecular insulating host. There is some contact. At 5% there'll be some contact, but it's relatively slow, and that helps us time things. So the upper panel is the panel you saw before. The lower panel is the photo-induced optical absorption spectrum. So we've hit the sample with a short light pulse above the band gap, and we look for changes in absorption. So we start in yellow, where you see quite a strong new signal just beyond 500 nanometers. That's an excited state absorption of the exciton here. And then that decays, and in its place grow the feature at 600 and the feature at around 800. We see both the electron and the hole. In other experiments where we use not an insulating host, but a host of carbazole biphenyl, the hole goes first to the carbazole biphenyl and later to the back to the TTM. So the feature here grows in quite slowly. We see the electron on the radical quite quickly. It takes about 30 picoseconds for the hole to find its way. Here it's very fast, but it is much, much slower when we have a CVP host. So we sort of tracked it out. Does that work in a photodiode? Well, I should mention this is the work of Piwei Li, finishing her PhD at the moment. Well, here are some, here is a test layer by layer organic cell. So we have ITO, PDOT-PSS as a charge collecting electrode for electrons, then rubrene, which is a similar band gap material, and then an evaporated layer of C60, and then some layers to allow electron collection. So this system shows quite good photocharge collection. The collection yields about 10% because only light absorbed pretty close to the rubrene interface produces excitons that get ionized between it and C60. But actually, we got more light collected, but I have to say we need some reverse bias voltage when we now switch to our radical system. So here we think we're getting, it doesn't matter where the photon is absorbed within the single layer of radical, we're able to separate charges. I have to say the short circuit efficiency is terrible, but with a reasonable applied reverse voltage, it's pretty good. And it doesn't matter whether we have C60 in or not. Those are the two upper levels, and the reverse leakage is surprisingly good. So it might be quite useful as a photo detector. I'm not promising it's a solar cell, but it's just a thought about where we can go with rearranging electronic structure with the organics. Well, let me move on briefly to some more spin things. Here we have a diradical. I'm sorry if the chemistry looks more and more appalling, but we have our two radicals, the two TTMs. They're now Baran connected through a fluorine, a metacoupled fluorine unit, so they speak to one another. They remain bright. You can see the luminescence coming out on the right. And the luminescence shows what is the primary emission, which is actually from the triplet, and then what is partly phonon shifted, but also has a different origin. It's a singlet emission at around 700 nanometers. So I should mention my student, Ritmala Chowdhury, who's this has been much of his PhD work. We had a wonderful collaboration with Alexei Chepelyansky and Ossé in Paris. These are measurements done in his lab, which he has a lovely dilution fridge with a magnet. So we're down at 0.25 Kelvin, at which point in no field the two spins have gone antiferromagnetic because there's a weak exchange. And the emission we see with no field is the red emission at 700. But if we put a few Tesla on, which they've got, the emission shifts to be the triplet, because we've now flipped the spins and we've now forced the selection to be triplet, and we've got that color change. So it's unusual to be able to have a dual emission system, and very nice that it's spin controllable. There are parallels, but not exactly the same physics as what is seen in the nitrogen vacancy center endowment. So again, it's that formation of that charge transfer state. By the way, on the right, the difference in the redox potentials is also about 700 nanometers, so that the energies seem to line up. So what about MV centers, and have we got something that might be useful as a bright sort of quantum device? And there's also very beautiful work from the Wasilewski group in Chicago, Northwestern. With some chemical modification, we now just have a meta-linked phenyl or pyridyl group between the two radicals. We have materials with similar luminescence behavior, but we've now got these spin-dependent effects, not at 0.25 Kelvin, but at room temperature, which makes them much more useful. And the huge surprise is that they show a very strong change in luminescence with magnetic field at room temperature and tiny magnetic fields. So we've measured up to 10% change in less than 5 millitesla. So this is fridge magnet territory. And that is surprising. There is, I will mention where there are some connections shortly. That's clearly connected with the fact that we have got triplets, and they intersystem cross to something slightly less emissive and redshifted, which are singlets. The magnetic field effect is evident. These are measurements of magnetic resonance measured through changes in luminescence. This is work done in Glasgow by Alistair Ingalls in the group of Sam Bayliss. And there you can see at zero magnetic field, resonances at around 50 and 100 megahertz, which with applied field fan out as they should do as we shift the energy levels with the Zeeman energy. So why are we getting these effects? Why is such small magnetic fields making such a difference? Why is this such an outlier against this huge literature on magnetic resonance of, say, triplets? Well, the answer is that most triplets are very spatially confined. It's in their nature. A molecular triplet will give you a D value, and therefore a magnetic resonance splittings, as you saw earlier for that anthracene system of gigahertz, many gigahertz. But here we forced the two spins to be quite far apart. We have built them to be about a nanometer apart. a nanometer apart, the D value, the splitting of the T0 from T plus minus, is about 50 megahertz, which is a few millitesla. And that's why we need very small fields to get the Zeeman energy to hit the D value, and that's what's giving the effect we're seeing. So the parallel, it's beautiful work of many years, particularly the work of Peter Hort in Oxford, exploring how photogenerated radical pairs in molecules in the back of the eye of European robin allow, it's the singlet triplet differentiation that gives chemical signals that allow these birds to migrate or orient from the Earth's magnetic field. Right, I'm almost finished, yes. So the magnetoluminescence we've spectrally resolved. So the black and red are with and without and with field. The differential signal you see in blue. These are measurements done in Paris. We can time resolve the luminescence and see where the change in time decay occurs. There is quenching of that redder emission on the 20 to 40 nanometer time scale. So that is from the excited state, T plus and T minus is going to singlet. There's a sign reversal at long times, which almost certainly involves ground state relaxation from the T0, from the S to T0 level. But we're unwrapping what's going on there. So let me finish with a little video. On the right is a sample which is glowing rather, a little bit of reddish light coming out. There's also some blue because it's a blue laser on it. And we're measuring the luminescence and displayed on the laptop screen. And if I advance the video, here is Ritu bringing a fridge magnet in the glass tube down to the sample, and you can see on the screen the magnetoluminescence is really, really easy to measure. And fridge magnets are cheaper than semiconducting magnets. Okay, it's so much easier to see a real demonstration, isn't it? So finally, I have to acknowledge various funding sources, particularly the ERC. I mentioned in the abstract that we've been doing some work on bioimaging. I'm not quite ready to talk about it, but it does look as though these molecules will happily go into biological material and retain their magnetoluminescence. So we think that these are going to be quite useful in that way. Far away from where I started, which is energy conversion for solving immediate energy, global challenges, but connected through that theme that if we can engineer luminescence, we're bound to find something useful. Thank you very much.
So, questions? You can just speak up.
Richard, congratulations. Very interesting to see this single material solar cell operation. This duplon state you're creating, what is the lifetime?
It can be quite long-lived. It depends how concentrated the material is, but we're out at microseconds.
Microseconds. Wow. Thank you.
I see one question. Or there. Carl.
Richard, thanks for the very nice talk. I have a question about the organic LED in this host guest system where the triplet is resonant to the doublet system. What is the voltage of the device? Where is the exciton generated in the host?
It has a threshold around 2.5 volts. It's not, I mean, it isn't a particularly voltage efficient device because the mobilities are not great.
Thanks.
A question. Who Robinson?
Thank you very much, Richard. Interesting. You talk in the radical carbazole compound, I don't know the name yet of it, but about the non-relative decays and how you engineer to remove that. But what about the optical transition? I mean, why is this a fairly strong optical charge transfer? I mean, the distance between the radical center and the carbazole is larger than I would expect. Give you give us a number for the.
Well, the absorption coefficient, I'm very bad at producing numbers, but about 1/5 of a strongly allowed absorption for the carbazole materials. For the materials without carbazole, such as the fluorine and the phenol, the absorption is weaker, and there is a problem that there is the transition is disallowed because there's a degeneracy between the transition from HOMO to SOMO and from SOMO to LUMO.
Does it turn into a photon-induced thermal electron transfer system?
The emission is just regular dipole matrix. Yeah, but you're right to be curious.
Thank you.
Thank you very much for questions and thanks for speaking. I call for the next speaker, Chihaya Adachi, to talk. His background is from the Center for Organic Photonics and Electronics, the research opera in Kyushu, Japan. We will talk about these topics.
Okay, thank you very much, Ole, for your kind introduction. So I'm so happy to give a talk about, today I'm going to talk about actually thermally activated fluorescence. Recently we found a very unique photophysical behavior of TADF around the zero gaps. So here you will see three typical TADF materials, POCZ-IPN, TMCZBO, and heptazine derivatives. These materials show very unique TADF behaviors. So today I want to highlight the difference of photophysical behavior of these materials. Okay, so let's starting from OLED. So the OLED is made of multi-layer organic thin films, Hall transport, and EML emitting layer and electron transport layer. So we forced to inject Hall and electrons. In the event of Hall and electron, so we have a 25% singlet generation and 75% triplet generations. So because of the spin statistics, so as far as we use the singlet excisions, we cannot get high efficiency. But triplet harvesting using triplets, so we can also convert singlet into triplet. So ideally, we can get 100% internal efficiencies. So, but not only fluorescence and phosphorescence, we have a third emitter, that is the TADF. So TADF, we forced to make a very small energy gap between singlet and triplet. We upconvert triplet into singlet and gets the emission as the delayed fluorescence. So now we can use the fluorescence, phosphorescence, and TADF. Actually, very first TADF was reported 1929. So and then actually 1926. So it's 100 years before it was discovered. So yeah, this year is a kind of anniversary of 100 years anniversary of TADF discovery. And then 1933, you know the Jablonski diagram. Professor Jablonski defined actually TADF. So light absorption, and then we generate singlet, and singlet decay to triplet, and triplet upconvert singlet again, and we have delayed fluorescence. So this is the mechanism of the TADF. So later, 1941, Professor Luis reported fluorescence showed the TADF. And 1961, Dr. Parker reported eosin Y also showed TADF activities. And 1970, benzophenone derivatives showed the TADFs. So very limited report. Every 10 years, very limited reports. And actually, efficiency was quite low. Yeah, 3%. But 2012. Actually, we have been working for the 10 years, try to improve the conversion efficiency. And the 2012, by using a POCZ-IPN, it looks very simple chemical structure. The chemical structure is composed of the dicyanobenzene accepting unit and 4 carboxyls. We can synthesize this molecule within 1 day. So it's quite simple. And then this material actually realized a small energy gap between singlet and triplet, 60 to 80 milli electron volt. So in this case, we can convert TDF into singlet and get the emission as the TDF fluorescence. So how can we design a TDF? So actually, we can find the material design rule in a university textbook, quantum chemistry textbook. Delta ST is proportional to the 2K. K is the exchange energy, and the exchange energy is given this formula. And this formula tells us we should separate homolumos. So then we can make a small delta STs. Very simple idea, just separate homolumos. But we need a light-emitting materials. Light-emitting property is proportional to the oscillator strength, and oscillator strength is given by square of the transition dipole moment. So here, transition dipole moment is given by this formula. So we need a large homolumo overlap. Otherwise, molecule never show the luminescence. It's completely contradictory requirement. So we have to separate homolumo to make a small delta ST. But to get high emission efficiency, we have to make an overlap. But chemistry is quite flexible. Okay, we can design a wide variety of molecules because we know the many donor and acceptors. So HOMO is tend to localize at the electron donating unit, and LUMO is tend to electron accepting unit. Okay, just combine donor and acceptors. We can make TDF materials. So then we synthesize more than 200 TDF materials, and we found that this is nearly 100 efficiency triplet to singlet conversion efficiencies. Okay, so this is an overview of OLED materials. So first generation is the fluorescence, and second generation phosphorescence, and third generation TADFs. So room temperature phosphorescence and TADF can realize nearly 100% internal efficiencies. Actually, 2019, TADF has been commercialized in a Taiwanese company, Wise Chip, and then still amount is small, but production is okay, now in the market. Okay, I asked ChatGPT how many TADF molecules reported so far. Around 2,700 papers published, and 25,482 individual property has recorded, and 1,318 unique TADF molecule has been already registered. So original structure is maybe around 1,000, and derivative is 10,000. TADF molecule has been developed last 10 years. Okay, so today's topic is the mechanism of the up conversions. So we try to understand how the triplet up convert into singlet. We collaborate with the Jean-Luc Belder's groups, and then Dr. Shankar Chen focus on our TADF force-set IPNs. Actually, if you look at these chemical structures, you will see 3 carbazoles. So carbazole is a highly bulky unit. 3 carbazole cannot move, but top 2 carbazole, this top 2 carbazole can move rather easily. So harvesting room temperature energies, 2 carbazole can move against the dicyanobenzene central unit. So Shankar, interestingly, he looked at not only S1 T1 energy, but S2 T1 S2 energy difference. Very interestingly, T1 S1 energy goes up with increasing a twisting angle, but T1 T2 S1 T2 energy becomes lower, and then virtually we can get zero gap formation at around 140 degrees. One important point is we can make a zero gap formation between S1, T2 energy levels. Okay, another point is the SOC, spin orbit coupling factor. So SOC between S1 and T1 is just 0.06 Kaiser. It's quite small number. But on the other hand, S1 and T2 SOC value is the 0.51 Kaiser. It's almost 10 times larger spin orbit couplings. So based on a small energy and formation between S1 and T2 and the large SOC factor between T1, T2 and S1, we understand basically T1 up convert to T2 and then T2 to S1. This is a probable mechanism of the up conversions. Actually, T1, T2, S1 up conversion is quite reasonable. This risk rate is well explained by the L-shade rule. So L-shade rule is given by top figures, top equations. K risk is proportional to the prefactor times Boltzmann factors. Of course, smaller the delta ST, we can accelerate reverse intersystem crossing rate, and prefactor is actually SOC factor. So larger SOC enhance the K risks. So T1 and S1 has a very similar wave function, but T2 is a slightly different wave function. So then we can understand we should convert T1 to T2 and T2 to S1. So this is a probable mechanism of the up convergence. I don't say probably T1 to S1 direct up conversion is also possible, but the probability might be small. Okay, and recently, quite unusual material, heptazine was reported by Professor Aizawa, Osaka University. Now he is in Hokkaido universities. He reported it's a negative gap behavior. You know the singlet is lower than the triplet. Triplet is lower than the singlet. But this kind of heptazine material show the singlet is lower than the triplet. It's a kind of a negative gap behavior. So he reported the delta density is minus 11 milli-electron volt. And they reported a very unique temperature dependence. I'm going to talk about this part detail. Okay, actually, heptazine, 2014, we also reported very unique behavior. GD reported the heptazine showed a very fast up conversion from triplet into singlet, around 240 nanoseconds, very quick up conversions. At that time, we reported this might be originate from a mixture of N-pi and pi-pi star that promote the very rapid up conversions. The quantum chemist, Professor Dong, Technical University of Munich, he calculated our material. Actually, he found our material is a kind of inverted materials. So here, S1 energy is 2.58, triplet energy 2.82. So that provide a negative behavior. 240 milli-electron volt singlet is lower than a triplet. This is because delta ST is not only electron exchange energy, but it's provided by some of the electron correlation energy. So correlation energy can be negative. Once we take into account the doubly excited configurations, not only one electron excitation, we should think about two electron excited states. In this case, electron correlation energy can be negative. So it looks like a violating of the Fund law, but this is a probable mechanism of negative gap behavior. Okay, consider IPM. Okay, let's look at the time dependence of the decay profile. You will see a very prompt decay, and then after that, you will see a delayed component here. So here, important thing is the temperature dependence. So phosphate IPN, longer the delayed lifetime at low temperature, but shorter the delayed lifetime at high temperature, because at high temperature, pipette is accelerate, and then it shows the shorter delayed lifetime. And you will see ISC rate is faster than risk rate. So then we can expect up conversion behaviors in case of the phosphate IPN. But heptazines, it shows a very strange temperature dependence. Okay, so here, so longer the delay lifetime at high temperature, shorter the delay lifetime, low temperature. It's completely opposite behaviors. In this case, delta still has a sign, minus 11 millielectron volt. We are very much concerned about these behaviors. Okay, and I also want to mention this very unique temperature dependence of the TMCGBO. So here, so this was observed in toluene solution, diluted solution, and then we observed the longer delay lifetime, higher temperature, and shorter delay lifetime at lower temperature. So this one, very similar behaviors. We are very much surprised. So we tried to explain. Basically, TMCGBO, when we disperse in a solid film, PPF, it's a wide band host, 38%, we observed very usual temperature dependence. So higher the temperature, risk rate goes up, and then activation energy is 13.4 millielectron volt. So in doped film, it shows the usual TADF behaviors. But in toluene solutions, it shows very complicated behaviors. So here, in the toluene solution, PLQI is 93%, and higher the temperature, longer the lifetime, shorter the lifetime at low temperatures. So this provide the actually risk activation energy is negative. Okay, minus 76.8 millielectron volt. So higher the temperature, okay, rate goes down. And ISC is the positive, 37.2 millielectron volts. So this provide delta ST is minus 170 millielectron volt. It's quite strange behaviors. Okay, firstly, we try to understand this behavior by experimentally obtain S1, T1, and delta ST. But here is lots of same experience. If we try to define S1, T1 energy from onset of, okay, like this one, the value is like this. Okay, toluene show the 7 millielectron volt, and other solvent show the negative delta STs. Okay, we also try to calculate S1 T1 with the threshold of 10 to the minus 3 and also 10 to the minus 4. So depending on the threshold, the S1 T1 value also fluctuating. So it's quite difficult to experimentally define, obtain S1, T1, and delta STs. Okay. And also, quantum chemical calculations, we apply the different functional and basis, and here you will see the 7 different functionals, and we obtain the variation of S1, T1, and delta ST. Even a calculation is quite difficult to get the accurate values. Okay, so we are very much puzzled, and if we have a problem, we always go back to the university textbook. And then, actually, we found a very possible mechanism in a physical chemistry textbook in Atkins. Okay, this textbook tells us there's a possibility of a negative activation energy. Okay, we have initial states and final states. This should be a positive. But if we have a additional reaction independent from a focused reaction, so this provides actually apparent negative behaviors, negative activation behaviors. Okay, this has been well recognized in chemical reaction between hydroxide and hydrogen bromide. So starting from here, the reaction goes to this direction, but simultaneously, if we increase the temperature, two materials start to separate, so reaction speed goes down. In this case, we can get negative behaviors. So based on this idea, we modeled in an exciton process. Actually, we have a T1 and S1. This is the conventional route. We also introduced the trap states. Probably this is T2. T2 state is provide the exciton trap states. So then we model this mechanism. Okay. So firstly, okay, so TMCGBO, this has more simplified CT and LE states. So S1 is the CT states, T1 is the LE states, and T2 is the CT states. Looking at this LE-CT relationship, actually T1 to S1 up conversion is possible because of the different wave functions. It has a larger SOPs. But T2 is a CT. So CT to CT transition is basically prohibited. SOC values goes down. So based on this model, we suppose, okay, this looks like a trap. We have thermal equivalent between LE and CT, and then based on the Boltzmann distribution, some of the exciton is trapped by T2 states. And then T1 to S1, this is the probable mechanism of the conversions. Okay, and we also introduced the temperature dependent of solvent polarities. So depending on the solvent, it showed a very strong solvent chromic effect. And we look at the temperature dependence of the spectrum, and we found lower the temperature, it showed red shift, longer wavelengths. So it's a bit surprised, but the experimental result tells us CT energy stabilization happened at lower temperature. So then we have a red shift. So we take into account this equilibrium and temperature dependence, solvent polarity effect, and we could well fit our experimental decays. Okay, so here you visit toluene, THP, THF, and DCM, and acetone. And we can all well fit with this experimental result with the theoretical models. In case of the toluene, THP and the THF, it showed the negative behaviors, but actually the delta ST is positive. In case of the DCM and acetone, it showed the normal behaviors, higher the temperature, shorter the lifetime, and this also provides the positive delta STs. Okay, so in case of the toluene, okay, so toluene is a kind of non-polar solvent. So CT, we can expect CT is higher energy level than LE. But if we use the polar solvent, like a dichloromethane, so CT state goes down and LE is higher. In this case, we can expect up conversion like this route. So depending on solvent polarity and the temperature dependence, so the transient decay is strongly influenced. Okay, so phosphate IPN. This is the positive gap material. And TMCGBO, this is nominally negative gap behavior. But in fact, this is positive materials. Okay, how about the heptagenes? Heptagenes show the, again, very strange temperature dependence. Lower temperature show the slightly shorter delayed lifetimes. So we tried to fit this material, and then, okay, actually, so Aizawa-san's paper indicate if we assume that the non-radiative decay from triplet is 0, so we can get the risk rate is faster than ISC. We get minus 11 milli electron volt. But if we assume non-radiative decay singlet is 0, actually ISC is higher than risk rate. It looks like a positive gap materials. In fact, we measure the temperature, low temperature fluorescence and phosphorescence behavior, and heptagene showed actually phosphorescence at low temperature. Yellow lines are phosphorescence spectrums. Okay, this is a temperature dependence of a spectrum and also transient decays. Methylene and THF and DCM, this show the normal behavior, normal TADF positive material behavior. Only toluene show the kind of opposite temperature dependence. Okay, and then experimentally we analyze that the ISC risk and ISC. In case of the K non-radiative decay is 0 from triplet state is 0, when we assume we get the risk is slightly higher than ISCs, and the toluene show the negative gap behaviors. In case of the KNR singlet is 0, we observe that the ISC rate is faster than risk rate. So looks like positive gap materials. But delta ST actually we can get the negative gap behaviors. So emission of the heptagene is very difficult to explain with a conventional analysis method. We cannot explain result, experimental result based on the conventional three-stage models. Okay, so finally, we introduced the same scheme, trap formation and the shift of the CT level by temperatures. And then, very fortunately, we could well explain transient decays. So based on this result, we could analyze that I only show today the KNR at triplet non-radiative decay is 0, and we found all solvent the delta is negative 4.3, minus 9.9, minus 11.6, all show the negative gap behaviors. Okay, so TAD heptagene derivative seems like a negative gap behavior, but just 4 milli electron volt, the room temperature 25 milli electron volt, is battery, looks like a zero gap materials. Okay, so TADF, very complicated photophysical behaviors, but we can categorize at this moment 3 different TADF materials. First is the, first is the IPN. This is the conventional positive gap materials. Second one is nominally negative gap materials. So the activation energy sometimes shows the negative, but if application of our model, actually this is the positive materials. And heptagenes, some of the heptagenes show the behavior of the negative gap, but 4 milli electron volt, very small gap. Okay, I want to talk more practical device. So TDF is very promising, but some of the TDF spectrum is very broad because of the CT emissions. So if display engineer look at the TDF spectrum, they said, oh, this is useless for the display applications. Okay, so then we forced to generate exciton at the TDF and transfer all energy to the terminal emitters. We use the Davna derivative. Davna is kind of a TDF, but we take advantage of the narrow spectral width as the fluorescence emitters. So the combination of TDF and the terminal emitter is very much promising. So our members optimized many, I don't know, maybe we made 50 or 100 devices, and then we could get the very nice behavior. EQ is 25, FWHM is 30. I think now the button is and LT95 is around 600 hours. Very stable device, we can realize. I think it seems like a good TDF as the, not the emitter, just for the exciton generators. Okay, we have a startup, Qlux, and they try to improve the commercial product. Now, as far as for the green, LT95 is 1,500 hours, and red emitter is more stable, around 2,000 hours. It's quite stable and ready for the commercial use. Blue is still a big problem. LT95, deep blue, this one 465, 220 hours. Still blue, we should get the longer device lifetime. But as far as for the CI coordination, the TADF, actually hyperfluorescent system, so the ideal largest triangle, green, blue, and red, providing next generation requirement for the next display application BT2020 requirement. Okay. Okay. Finally, I'd like to thanks to our members and also the funding agencies. Okay. Thank you very much for attention.
Thank you very much. Paper is open for discussion.
Question.
I see one question over there.
Yeah, thank you.
Inside. Miyazaki.
Yeah. We understand the strong solvent polarity effect on up conversion. The up conversion also can be done in solid state. Solid state. You show the device.
Yes.
That up conversion is including solid state also.
Yes.
Really?
Yeah, today I only show the or discuss for the inner solution solvation effect, but solid film showed most of the in the guest host systems. It showed a very strong solvation effect. Looks like a similar environment in a polar solvent. So it shows the CT state always goes down in the solid films.
But solid state, there's no solvent inside, and how is the efficiency of the up conversion efficiency? Is lower than in the
Yes,
solution state?
it depends on the materials. So we can design material optimized for the more polar solvent. So then it shows the higher efficiencies. Even in a guest host system, we can get nearly 100% up conversions.
Oh, thank you.
Anna Köhler.
On slide 21, you did show your phosphorescence and the fluorescence from the same compound. Were they actually taken at the same temperature? Or was the phosphorescence measured at low temperature and the fluorescence at high?
Yes, actually, yeah, actually, yes. And but most of the fluorescence, very small shift of fluorescence. So then, yeah, we also take into account this part.
So you take into account that your position shifts with
Yes.
temperature.
Yes,
And don't compare different temperatures.
yes, yes.
That's what I want to
We
know.
delicately we measure the shift of the fluorescence. Fluorescence in this case, fluorescence slightly show the red shift.
Yeah.
Also, we also carefully check the absorption spectrum. Absorption spectrum is also slightly changing with the temperatures.
Do I see further questions? I do not see that. Thank you. Well, Richard, sorry.
Fantastic talk. One of the remaining issues is lifetime, particularly for blue. Naively, a long relative lifetime, or a long time for the excited state before photon emission, is a problem because it makes more time for exton-exton collisions, which can produce a very highly excited state that is thought about as being responsible for long-term damage. Is that a correlation you've seen with your systems?
Yes. Okay. As far as for the green emitters, we systematically look at the relationship with lifetime and triplet lifetime, device lifetime and triplet lifetime. We can see a very close correlation. So shorter the triplet lifetime provide longer device lifetime. That is true. But as far as for the blue, we try to make shorter triplet lifetime, but still stability is not so.
Okay, let's thank our speaker.
Call on the next speaker, Paul Blom, from Max Planck Institute for Polymer Science, I guess it is. So, there's your title.
Okay, first of all, thank you for inviting me. It's a great honor to be here, and also an honor to be in this lineup of speakers. So today I will talk a bit about OLEDs, but basically single layer OLEDs, and on our way towards to make them efficient. So I will give you an introduction, then I will tell you what we did to get rid of trapping by defects, and then some challenges we have. So the work started in 1990 with the discovery of the polymer light emitting diode in the group of Richard Friend. And that was basically a very fascinating discovery in the way that the device, the device was extremely simple. So it was just glass covered with ITO, then a polymer layer from solution, and then a cathode, which is typically calcium covered with aluminum or barium with aluminum. Then you apply a voltage between the bottom and the top contact, and then you get the light emission. I did my PhD in gallium arsenide quantum wells, so also light emission, and that's what I was used to. And this, like a molecular beam detection machine, so it has a pressure inside smaller than 10 minus 10 millibar, and the slightest defect would kill your device. And then you see here on the left, you see this. So you see a pipette with some liquid, and you make a device and it lights up, which was like, you know, fascinating. Could not understand at all why this could even work. So in the early 90s, so this dream of solution processed electronics came up, and something what was told a lot was, can we replace this fancy IC factory that costs billions, like by a print shop? So can we roll-to-roll print solar cells, or can we inkjet displays? Because that would dramatically reduce the cost of fabrication if this would be possible. If you, let me see, yeah, here we are. So this is, I hope that the movie starts. Maybe I need some assistance from above.
Peter?
Maybe one slide back. Just can you look here if the movie starts? Yes. Yeah, thank you.
Mm-hmm. No. Mm-hmm.
No, it doesn't start.
Mm-hmm.
I had here a movie of the inkjet printers we used at Philips at the time. Normally I go with the mouse on that little arrow.
It says it doesn't find it.
No.
Oh, okay. Well, sorry about that then. So already in 2004, so more than 20 years ago, there was an inkjet printed display shown but it never made it into the market. It was back then also based on polymers, but the problem was that the efficiency was too low. So the external quantum efficiencies was typically a few percent. The device structure, as I said, was very simple, just as a single organic layer between two electrodes. But in parallel, the OLEDs became more complicated and followed basically using the vacuum deposited molecules, like you heard also before. And as you can see in this picture, the stacks got more complicated. So you have hole and electron injection layers, you have transport layers, you have the emission layer, and you also have exciton blocking layers. So you typically talk easily about 6 to 7 layers, of which some layers also have more than one organic molecule inside. So there are many compounds. So it's quite complex. But by using phosphorescence, as we also heard, so that you harvest triplets, the efficiencies are quite good. So the external quantum efficiency goes down to like 30% or so. The limitation that is still there is that you have to outcouple the light, so there's a lot of internal reflection. That's why it's not 100%, but 30 or so. So actually, when you look on your TV, then it gets even worse, because you don't have a pixel. It's just not one of these stacks, but there are 3 or 4 stacked on them, so a so-called tandem structure. This is from a press release of LG. You see here to make white light. They stack 4 OLEDs, and the reason is actually simple. So blue is a problem. So if you stack 2 blue OLEDs, then means to get a certain light output, you only need half of the current. And half of the current means that the device lives longer. So the main reason to stack a couple of OLEDs on top of each other is to overcome the stability issue, especially for blue. But of course, then the structures get extremely complex. And I showed also here from a press release of NG, they invested in a new factory of 9 billion to make big TV screens. So it's still far away from the print shop that we once envisioned. Now you can say, okay, is then solution processing completely dead? No, it's not. So there is still a company in China developing inkjet printed displays, but they also use the multi-layers. And also here, you can see from a press release, they invested over 4 billion to develop inkjet printed displays. So our idea was always fascinated by the early devices of the 90s, that in the ideal world, if you would print a device, it would have only like 1 layer or so. So you don't have to worry that 1 layer does dissolve the layers underneath and so on, and it would things made very easy. So what we worked on is single layer OLEDs. Now, why would you work on that? As I said, you can look at it from a cost perspective, then it's a simple structure, it would be printable, would be cheap, and so on. For us as scientists, a single layer OLED has also a lot of advantages, because it's much easier to find out how it works compared to an OLED with 7 or 8 layers. So doing device physics is more quantitative. But if you then think about it a little bit further, you basically realize that a single layer OLED can outperform a multi-layer OLED in the way that, because first, when you don't have these layers to confine charges in the emissive layers, so blocking layers, then if you don't have that, your device will operate at a lower voltage, which means if you would in theory have the same efficiency, and then a lower voltage means you consume less power. So a single layer device is then more energy efficient than a multi-layer stack. The other thing is that in a single layer device, the emission zone is spread over a much larger distance than in a multi-layer stack, which makes it more stable. So you have less, lower concentration of triplet excitons, of charge carriers, and so on. So if theoretically you could make a high efficiency, then you can in principle make a device that is more simple, more cheap, more stable, and consumes less power. So that sounds good. But the big question is if. Can you make an efficient single layer OLED? Now, of course, we investigated why is it so low. Basically, there are two main reasons. One is in the first generation of the polymer LEDs, we did not harvest triplets. That was, of course, already known from the start. But the second layer is that the organics, they have defects, and they trap carriers, and that's very bad for your efficiency because you can have non-radiative recombination. For example, if an electron is trapped by a defect, it can recombine with a hole, and that's a non-radiative process. Also, when you create an exciton can diffuse. If it finds a defect, it will decompose. So it lowers your photoluminescence quantum yield. And third, if you have a lot of traps of one carrier, and the recombination zone switches to close to an electrode, and there you have a lot of losses because you transfer energy from the light to the metal. Here you see some papers that we published some of these effects over the years. The first problem of triplet harvesting has been addressed by Richard and by Chihaya, and actually we were extremely happy, so to say, when we did see these papers, because then we realized that in principle one of the two problems is solved, and that if we would make a single layer device, that we do not have to worry anymore about the triplet harvesting. So that would be good. And then the main question would be to get rid of the trapping. So it's basically a very old problem. So this is a paper from 1996, so it's 30 years anniversary, where we showed back then that in a conjugated polymer, PPV, that the electron transport is much worse than the hole transport. And what is typical for trap-limited currents, here you see the IV on a log-log plot, is that a trap-free current typically is quadratic. That means on a slope, on a log-log plot, it has a slope of 2, while a trap-limited current has typically a much steeper slope, like the trap-limited current is, for example, v to the power 5 or v to the power 6, which is then here the slope. You see there are many orders of magnitude difference between the electron and the hole current. It's a logarithmic scale. Now, to understand that, we first had to understand the transport of the carriers that are not in a trap. And here we basically built on the work done by Heinz Bessler for many years, showing that energetic disorder is very important, which basically means that if you have an organic semiconductor, you don't have a discrete HOMO and LUMO level, but there is an energetic spreading due to disorder. And what we also showed then was that the mobility in an organic semiconductor depends strongly on how many carriers you put in, because if you only put a few, they relax in the tail of a Gaussian distribution, and then it's difficult for them to escape, so it's a low mobility. If you fill it up in an OLED, that means you go to higher voltage, then the mobility goes up, and then the transport gets more easy. And based on this, together with the group in Eindhoven, we then made a model, which is now called the extended Gaussian disorder model, that can nicely describe the current voltage characteristics of organic semiconductors in general if they don't have traps. Now, with regard to the electron trapping, we observed something funny in a way. So we also, next to OLEDs, we worked on organic solar cells, and they had smaller band gaps typically. And what we noticed was that when compared to vacuum, the position of the LUMO level got lower, that the slope of the trap-limited current also got lower. And you can explain that very easily by assuming that there is a universal trap located at an energy of around 3.6 eV. And if your LUMO of your organic semiconductor goes below that level, there is no trapping at all. So all the semiconductors with a LUMO deeper than 3.6 eV, they don't have trapping, electron trapping. And the group of Peter Ho in Singapore, they did spectroscopy, and they found that basically oxygen that is hydrated has exactly an energy of 3.6 eV. So this is potentially an impurity that traps the electrons. we also looked at the recombination mechanisms. Already again by Heinz Bessler, he already showed that the bimolecular recombination is a so-called Langevin process, which is dominated by the sum of the carrier mobilities. Basically, it means that the time that the carriers need to recombine is the time that they need to find each other. And we also showed that for trap-assisted recombination, so an electron in a trap recombining with all, that is the same expression, except that you put one mobility to 0. So what that also means is, if you measure the mobilities, that means that you then also already know all your recombination processes. So that means to model the OLED, you don't have any free parameter anymore. Regarding exciton diffusion, we also worked together with the group of Quinn in Santa Barbara, and there we found that that basically the exciton diffusion length was always half the distance between the traps. So what it means is that when the amount of traps is lower, then the excitons can diffuse more, and basically, so when you optically create an exciton, it diffuses around until it finds a trap, and then it disappears. So that means that both the diffusion length as well as the decay time of the fluorescence are all trap dominated. So it has nothing to do with the intrinsic properties in principle. So then we also looked on the optical outcoupling. As I said, you can reach typically efficiencies in the order of like 30% or so if you don't do any special tricks. And what you then see is indeed when you have traps, in this case electron traps, then what happens is that the electrons get trapped close to the cathode, and this is where all the light is generated. And when you don't, and then your outcouple efficiency drops dramatically. So what we learned over the years is that if you have a system with a lot of traps, like the old polymer LEDs, and that your EQE, your external quantum efficiency, is a few percent. If you then would harvest triplets, you can reach something like 10% at best. But if you then also can get rid of the trapping, you could reach numbers close to 30 in theory. So now what can you do? Of course, you can say, well, if there is this trap level at 3.6 eV, I basically redesign my semiconductor. So I move the energy levels down and I put the LUMO around 3.6 eV. The problem is then that the HOMO gets very deep and all our organic anodes don't work anymore. So we get, instead of an electron trapping problem, we get a hole injection problem. That can in principle be solved because it turns out when you use oxides like molybdenum or tungsten oxide, and you put a very thin tunnel barrier between the electrode and the semiconductor, that you can make very nice ohmic contacts. That sounds a bit counterintuitive. What is counterintuitive is that the HOMO of the tunnel barrier has to be deeper than the HOMO of the semiconductor. So in order to improve injection, you put a material in between that has an even deeper HOMO. But the reason is that this electrode pins on this position, and then so basically you shift it with respect to the semiconductor. Here you see experiments where we use CBP as a whole conductor with an HOMO at 6 eV, and by using these interlayers, typically a few nanometers thick, we can make ohmic contacts. If you leave the interlayer out, you get this dashed line. That means that it's an injection barrier on the order of 0.4 eV. And if you would use P dot, you see you can't inject at all. So this is a nice way to make ohmic contacts on semiconductors with deep HOMOs. And then we came in the end to this picture. So here is again the slope of the IV curve on a log-log plot. Remember, big 2 means no trapping. Big slope means a lot of trapping. What you see is, now in green are the points that I showed you before of polymers, in red are small molecules. Now you see when you lower the LUMO, you get trapping, less trapping, until 3.6, no trapping at all. Then the whole transport, this is the HOMO level, no trapping until you reach 6 eV, and beyond that you get trapping. And we think that this trapping is from water clusters. So here you have a problem with oxygen. Here you have a problem with water. Now, what can we do? Of course, at the first step we did, knowing this, we said, okay, we take now a material that has the LUMO at 3.5 and the HOMO close to 6, so right at the edges of the window. And this is a TADF material, like Chihaya explained, you harvest triplet excitons with reduced singlet triplet splitting. And indeed, if you measure the hole current and the electron current separately, then you see that this is quadratic and there is virtually no trapping. So for both electrons and holes, and even the mobilities are quite equal. So this is a yellow emitter. We also didn't use a host here, so this is a pure TEDF film, no, just one component. It had a PL quantum yield close to 90%. Came from this paper here published in Nature Photonics in 2008. And then indeed, with this very simple structure, we got an EQE close to 19%. So basically, from device physics point of view, it's a single layer device because you have two ohmic contacts with one layer as an emitter. From fabrication point of view, you can say, well, there's still 3 layers because you have 2 tunnel barriers on each side. So, but still, what it showed us is that indeed, that if you reduce the trapping a lot, that the efficiencies go dramatically up. And as I said, because the operating voltage is low, we got 10,000 candelas at 3 volts, and that you get a very good power efficiency for this device, and like 90 lumens per watt. What you can also do from device point of view is you can say, okay, I take a TADF emitter, and in this case, this DMAC-BP. It has, like you expect, it has good hole transport, bad electron transport, but I can also flip the device over. But then you need, you need a cathode that has to be on the bottom that can be spin coated. And here we collaborated again with the groups of Lele Chua and Peter Ho in Singapore, and they developed this N-type doped polymer that you can use as a cathode. What you then indeed see is that for the normal device you get an efficiency of around 8%. But for the inverted device, you get something like 16 or 17%. It even goes up to 19% if you, the outcoupling efficiency goes up to 19%. And if you then look on the photoluminous quantum yield, you end up on a device efficiency of 16 or 17%. Of course, the challenge is now to make a blue OLED, because that doesn't fit in this window. And at the blue emitters, they typically have a HOMO at close to 6 eV and a LUMO which is far out in the trapping regime. So all these blue materials, they have typically very severe electron trapping. Now what we did here, what we realized is that carbazoles, they have a HOMO level of around 5.8 eV. And so that means they are not susceptible for hole trapping. This is a donor acceptor molecule where the HOMO is on the carbazole and the LUMO here is on the triazine. So we were interested initially in the charge transport, that if we would use a triazine acceptor and then increase the amount of carbazoles. So this is like this, the 4CZ-IPN from Chihaya, and we went to 4 and even 5. And what we noticed was that 4 of these components have a trap-limited current, and 1 component doesn't. And that's the one here with the 3 carbazoles. It shows a nearly trap-free transport, although the LUMO is quite high up. And what we think, what our proposal is, well, we know that these molecules, they make dimers. And what happens is if you have 1 carbazole, and then they make a dimer where the triazine aligns, and the carbazole is like shifted over 60 degrees, so it's a bit like this. But if you have 3 carbazoles due to steric hindrance in the dimer, the monomer is flipped over 180 degrees. Now in this case, the electron transport goes like this, and you have a very open structure that can easily be attacked. But here you have like, well, I would almost say like a coax cable, where the electron transporting core is protected by carbazoles all around. That's the basic idea. But this is just one example. In the meantime, we made many more structures, and we have now a whole range of trap-free organic semiconductors. So here you see the current voltage. So you see here the hole current and the electron current. They are both trap-free and equal. So for me, I published this a few years ago, this was the first time that I did see a large bandgap organic semiconductor that had no trapping neither for holes or electrons. And as a reference, here you see an electron transport, a typical electron transport layer, TPBI, that is used in OLEDs also. You see, due to the trapping, it's a few orders of magnitude lower in current. Now what you can do with it, for the material itself is not such a good emitter, but you can again use this DMAC-BP, which is a green emitter, like I showed you before, has good hole transport, bad electron transport. Efficiency is below the 10%, around 8%, like I said. But then what you can do, you can blend it with our material. So the lumos, they are closely aligned. And what happens here is that the electrons, they stay in this material mainly, while the holes are in this material. By playing with the composition, you can very nicely balance the transport. It's trap-free, and then the efficiency goes up to 20%. Which also is remarkable, is that for DMAC-BP, all the multi-layer stacks are published are all around 20%, but they all have a power efficiency of 50 lumens per watt. Our simple device has a power efficiency of 80 lumens per watt because it works at a lower voltage. Now this is then the next step. So we looked then at materials that were optically better. We found again one in the literature. So it's this Spiro compound with again triazine as an acceptor. And it's a bit light blue, sky blue we call it. What you see here is that the structure is even more simple. So it's P.PSS that is slightly modified, then a blend of two materials. So this is the emitter in a 1-to-1 ratio with a host, and a barium aluminum electrode. So this is really exactly the same structure like the old PLEDs that we used to make in the 90s. And this one has now an EQE of 28%. And according to our outcoupling calculations, that's also the maximum. So we think that the internal quantum efficiency of this single layer device is 100%, which means that every charge carrier that is injected is now transformed into light. So from electrical point of view, there's nothing we can do anymore about it. We only have to now look that we can improve the outcoupling further. So the stability of this device is not so good, but for us it was important to show the principle that it is possible with one layer to make a 100% efficient device. That was for very many years an open question. Now the challenges, as also Chihaya mentioned, because TADF have a charge transfer emission, they have a broad emission spectrum. And he showed already that what you can do, you can put a fluorescent dye inside and it's hyperfluorescent. But for our single layer concept, that doesn't work because after many years to work of getting things trap-free, what we would do, we would induce traps. Because by definition, to get energy transfer, this one has a slightly smaller bandgap than this one. So then another problem is that when the biggest problem actually is when an electron, for example, is trapped on the fluorescent dye and it recombines then with a hole, you lose your selection criterion. So you get again 75% triplets. So it doesn't work. So we use the same emitter, this multi-resonant TADF, the DAPNA, like Chihaya showed. We put it in another blue TADF host. And then also in a inert large bandgap host. So in this case, there are three components, of which this one is around 1%, and the other one are close to 1-to-1 ratio. Again, this DBADI, this TADF host, was reported in literature to have a good EQE in a multi-layer structure, 28%, and also a relatively decent lifetime for a blue TADF material. And what we made use of is something we learned a long time ago. As I told you, the HOMO and the LUMO, they are Gaussianly broadened due to this order. And when you have a trap normally, then when that is in the band gap, it's a trap. But when it is above a certain level in the Gaussian, then it participates in the transport. It's not a trap anymore. So there is a small offset that you can have between the maximum of the LUMO and the trap. So you basically use here the fact that there is energetic disorder. That's what we did. And so we inserted this dye. And then what we saw was that the efficiency of the device with and without the emitter is the same, about 25%. The power efficiency is good, but now what you see is that the spectrum is blue shifted and narrowed. So it's the spectrum has a half width of 22 nanometers. It's blue, it's not yet deep blue, but bluer. And also the lifetime we reached is about 800 hours for the LT50, which for blue TADF is already quite a good number, but not good enough for applications yet. Maybe in the last few minutes. So, of course, we also in the past thought a lot about using OLEDs for lighting, but you can imagine that you cannot use a 30-layer stack for a lamp. So the whole multi-layer evaporated stack is just too expensive for normal lighting. So you would need something like solution processing and roll-to-roll processing to get the price at least in the right area. Again, same problem. You make white light, for example, by putting a red or an orange dye in a blue matrix, and no matter how you align it, you get trapping. And in principle, you need only 1% of the dye. That sounds like little, but that's a large amount of traps. It's like over 10 to the 18 per cubic centimeter. So what we did here is the collaboration with the University of Cambridge, the group of Hugo Bronstein. We make use of the fact that if you have trapping, that this is a short-range process. It's like hopping between two molecules. It takes place over 1 to 2 nanometers, while energy transfer takes place over a longer distance, more like 8 to 10 nanometers. So the idea was if we have an emitter that is somehow protected by some kind of isolating shell, and then we could, in principle, block charge transfer, but we could still allow energy transfer. And the group of Hugo Bronstein and the Cambridge group, they published this kind of emitters that they used basically to avoid texture transfer, which is a process very similar to charge trapping. So we contacted them and asked them, can we please look at the charge trapping behavior of these kind of molecules? They even made new molecules for us. So this is a more greenish yellow emitter. And what you see here on the energy scheme is that when you put it in a blue host, and that both the holes and the electrons should be trapped. But when we look here on the current, this is the hole current and the electron current with and without the dye, we see that they're all on top of each other. So we can insert 1% of this material, and we don't change the charge transport, which is quite amazing, which basically means that we can also change the spectrum while keeping the efficiency of the LED the same. So that means once we have a good blue matrix, we can make any color by just putting a little amount of dye in without losing efficiency. So there's no trapping. Now the last, so this is just wanted to show you if we look at one TADF molecule, these are the amount of experiments that we need to do. So we make charge transport measurements, we can simulate the OLED, but then we know locally where the electrons and holes are and the recombination. And we do time resolved spectroscopy that gives us the rates of intersystem crossing and reverse intersystem crossing. And if you do that as a function of intensity, you get also rates for the annihilation process. We have a model for outcoupling. If you bring that all together in the end, you can model the external quantum efficiency. And then, and here you see on this picture, you see the experimental one and the modeled one. In this case, we see there for OLEDs with different thicknesses. And what I would like to stress is that this model has no input parameter. So everything has been experimentally measured. There is no fit parameter or anything in there. So now why do we do this? Because we want to, that's the last problem we have to solve, that's the stability. And I show you here just one result. Here we measured the the lifetime where the light dropped to 80% for different light intensities. And now what you typically do in what people often do in the OLED world is that they have some kind of empirical formula which has an acceleration factor, because you cannot do a lifetime test for 10 years. So what you do, you measure at very high light intensities to shorten the test, and then you extrapolate to daily use. And for that there is an empirical formula. But in our case, we have good reasons to believe that for this device, triplet polaron quenching is the dominant mechanism. So what that means is that you create charge carrier traps because some molecules, they fall apart. And that means we have one fit parameter at one light intensity that links the amount of traps that you create to the amount of carriers and excidons. But then with that one parameter, we can then calculate at every light intensity. That's what we did here. And you can see that we can fully reproduce this behavior. So in principle, we would only need a test at one light intensity to measure one unknown parameter, and then we can tell you at every light intensity, every sample thickness, and so on and so on. So that's what we are working on right now. So with that, I come to the end. So if you have typical organic semiconductors, it doesn't matter if they are spin-coated or evaporated. There's always some defects related to oxygen and water. So you can make trap-free transport by stacking the molecules in the right way. And we realized a blue single-layer device with 100% inner quantum efficiency by getting rid of the trapping. And we can also convert colors in OLEDs without trapping, and therefore with lots of efficiency. So I'm still hoping in the next years that we can still manage to at one time come with cheap OLEDs that have one layer and our solution processed. So, and these are the people in the institute that did the work. We collaborated with Peter Ho, the inverter device with Quinn in the past on the exciton fusion. And I thank you for your attention.
Questions, comments, reflections? Carl?
Thanks for the very nice talk. You mentioned that you have a broader exciton generation zone.
Yeah.
This might be a challenge for better outcoupling. How does that balance?
Yeah, so what you normally do in a multi-layer stack, you put the emission zone in the position where it's maximum. What we did model and also did measure is for example, if the maximum point is 30, and we have I have it not in the talk. If you manage to get the maximum of your distribution more or less close to that point, then you integrate it, you end up on 28. So we stay like 2% below the maximum value of the distribution. But under the condition that you get the recombination zone in the right place.
Paul, I very much like this concept of designing materials for prep-free transport. What is the temperature sensitivity of the prep-free transport? So if you go to lower, higher temperatures, do you see then any asymmetry in the tails and the absorption tails, or is it insensitive to temperature?
Yeah, so then what you basically see is you get the same temperature dependence like we know from the trap-free transport from inside the window where everything is dominated by the amount of Gaussian of the energetic disorder. So that model then simply works. But if you have trapping, actually, I did not talk about it now in view of the time. When you have trapping, you reduce the temperature dependence. That puzzled us for years, but we later understood. But it's nothing, no, it just behaves like a trap-free material. So.
Richard?
Paul, beautiful talk.
Thank you.
The avoidance of electron trapping requires this organized structure.
Yeah.
Does that require crystallization, or is that still present in a amorphous structure?
No, we think there are nanocrystallites. We think. So there is some form. We did solid state NMR, and we could see two signals. So one from, let's say, a little bit more crystalline phase and one amorphous. So we think there are very small nanocrystallites.
I do not see any further questions just now, which means that we can thank our speaker.
Good noon, everyone. And it's my great honor and pleasure to come here to introduce our work. Let me familiar with okay. And today my talk will include quite a few topics. I mean, small topics. And none of them will be discussed in very good depth. But I just want to show some potential and to get some interest from you. And about 70 years ago, so two scientists invented this device. They use the P-type material, copper, the mechanism PC, and the TMDA to use mechanical pressure to build the sandwich structure. And they observed the photo effect, from the organic device. And after that, about 40 years passed, and the solution process for OPV cell was reported. And here, they use the polymer donor, it's PPV and the same PPV, or polymer donor blended with the fluorine acceptor. And for the solution process device, the fabrication cost is very low, so attract a lot of interest. And typically, the material in the organic solar cell can be categorized to three types. The first type is for the homopolymer blended with fluorine. And the second one is DA copolymer blended with PCBM. And recently, the DA copolymer blended with ADA, a small molecular acceptor, over 20% efficiency has been realized because the absorption band for the ADA type small molecular acceptor is very good. And however, for the homopolymer P3T, so for this blend only cover a very narrow band of solar light. However, for the DA copolymer blended with PCBM, the sunlight within 800 nanometer or 900 nanometer can be utilized. And if we talk about the OPV technology, we need to think about the three key parameters. One is efficiency, another is cost, the last one is stability. And for the efficiency, recently, my group reported these results. We built the tandem OPV cell with a 21.7% efficiency. The scientific point in this paper is not very strong. However, I think it looks like art, because if you want to realize a very high efficiency for the tandem solar cell, you need to make the subcell and the interlayer very carefully. And in this paper, we utilized the broadband material for the PB2 blended with FTCC bromo, and to build the front cell to get the high VOC for the high energy solar light. And we use the PM6. Where is the pointer? PM6 and BTP EC9, and plus this one, these three components to get the real cell. Basically, for the real cell, for the single cell, over 20% efficiency can be realized. However, when we build the I mean the tandem cell is only 21.7. Yeah, it's very difficult to do, but yes, efficiency is a little bit higher. And for the interconnection layer, we utilize the IPA processable P dot, and to combine with NDI based N-type interface layer. And more recently, we also report some, low-cost polymer donor and low-cost small molecular acceptor. For instance, so for this polymer PTVTT, so we utilize the Easter group to make the conformation of the backbone more stable, and to realize a very strong aggregation effect in the solution state. Where's the pointer? Yes, very strong aggregation effect in the solution state. And then when we spin coat the neat polymer onto the substrate, we realize that a nanoscale aggregation very easily. So when we blend this polymer donor with different acceptor, so you can realize a quite good efficiency. Not as high as PM6, but still quite good. And for the small molecular acceptor, for this one, TBT26, so the core unit is only 3 aromatic ring. And the synthetic cost for this one is quite low. However, for this one, for this small molecular acceptor, only yield quite good efficiency when it blended with PBQTF. So, which means the compatibility of this small molecular acceptor is not very good. And we coat the large area, the small area module, and realize about 14% efficiency. And another question is, can we realize high efficiency based on a low-cost donor and a low-cost acceptor? So the answer is like this. So we blend PTVT-TBT and with another non-fused small molecular acceptor, realize about 14% efficiency. So, and recently we reported this work discuss how to define the low cost for the organic photovoltaic materials. We think the MOC is quite a good concept. So material only cost. We need to trace back the raw material to kilogram scale, commercial available material, and then to calculate the cost. And also you need to put the efficiency here with the chart, and to get some idea for the low cost part. And when we talk about the stability, so that's include two parts. One is the chemical stability, another is the morphological stability. And for the chemical one, so we need to think about the UV light, because UV light can make the photoactive layer decomposed. So in this work, we try to use the NDI-based small molecular interface layer to modify ITU and to make a stick layer, and to use this layer to convert the UV light into current photocurrent. And like you can see here, so the absorption is the red curve. So all of the UV lights can be absorbed by this material, and then you can build the photoactive layer onto this. So as shown here, so if you use the UV light to illuminate the device, you observe the quite good current density, which means this device can convert the UV light into current photocurrent, and that's why. So the stability of this of the solar cell is quite good. And another issue for the stability is like moisture, because for the sandwich device structure, so we use the hydrophilic material to modify the ITU, and then to use the hydrophobic photoactive layer spin coat onto the the interface layer, which means the moisture will enriched in between the two the interface between the two layers. Therefore, the the device performance is very sensitive to the moisture. So to solve the problem is we need to design the hydrophobic material to modify ITO. However, we also need the the interlayer to be robust, and because you need to use the chloroform or chlorobenzene to to coat the active layer onto the interface layer. And in this work, we use the cross-linkable functional group introduce the NTI interlayer and to spin coat this material onto ITO and use the cross-linkable condition to get the very robust layer. And in this material, we use this dopant to get a very high conductivity. And the result is like this. So as you can see here, for the device, if you store the material, the device into the glove box, so for 1 month, so the stability for the two devices is quite similar. However, if after very simple encapsulation, so the new device is quite good. And if you put the device into water and then to test the device, so as you can see here, so after 200 days, the new material modified the device, the stability is quite good. And even you can, put a device without any encapsulation and use use the sunlight and to test the device. So the result is like this. So for the zinc oxide or the other type of material modified device, so the device performance drops, completely after 10 minutes or 15 minutes. However, for the new material modified device, so after 10 hours, so still work. And if you give the device a little bit encapsulation, so after 10 hours, so almost no change. And also the burn-in part, so completely removed, because when you put the device into water, the temperature will keep at 20 degrees, very easy. And if you make the device with the encapsulation in the air, store, for the continuous illumination for 50 degrees, so after, almost 5,000 hours, so the device performance is still quite good. The burn-in part is very fast, and the other part is very flat. And let's talk a little bit about the competitive features, because OPV, cannot compete with other photovoltaic technology for the outdoor application. So we need to think about a little bit more about the unique features. The first one is for indoor application. So in 2019, we collaborated with Professor Feng and reported this work, because we can rebuild the molecular structure of the small molecular acceptor and to make the photoactive layer to give a very good absorption for the indoor light, and then to realize quite good efficiency. For the outdoor, for the 4 square centimeter device, you realize 23% efficiency, and the device for the outdoor is about 10% efficiency. And in 2022, we reported this work. So we spin coat, we blade coat the device. Layer by layer, and realize a quite big device. It's a 100 centimeter for one cell, not a module. So one cell. So the efficiency is about 23%. So which means OPV. So we're very good candidate for indoor application. And another question is, so can we make a OPV device? Compatible for both indoor and outdoor illumination? The answer is like this, because for the indoor sunlight, indoor light, is very different with outdoor sunlight. So we need to make a compromise, for the absorption. So after the modulation of the molecular structure, we get the absorption in between here. And for the under standard solar light, the efficiency is about 15 something. And for the indoor light, is still 20%. So OPV can do a lot of things. Another interesting thing is like this. So when we do the, for the indoor application, so we make the device like this. And also the device can be used as a LED. So the light is very bright, although the EQE is not very high. So I don't know how to use this device, but the feature is very attractive. And another one for OPV cell, for the application is like this. Let's imagine about the wireless energy transfer. So for the military application, we need to think about, very high current density. So for this part, silicon and gallium arsenide solar cell is quite good for this application. However, for the low current density part, for the small, for the low energy consumption electronic devices, OPV cell quite good because you can tune the color of the light beam, to deliver 1 watt, power, electricity power, within 10 meters. And for instance, after we modulate the device and the material, so realize about 33% efficiency. For red light. So for the requirements for the wireless low power transmission, we need to think about choose a wavelength with sufficient high EQE and also minimize the energy loss by adjusting the wavelength of the beam light. And also you need to think about the laser and the monochromatic light source should be very cheap. And after that, you can get a quite good efficiency with very low cost. And in our results, we realize about less than 40% efficiency. However, if we can optimize everything very good, over 50 or over 60% efficiency can be realized, which means you use a 1 watt, beam light, and over there you can get a 0.6 watt electricity output, which were very interesting. And the last one is for the underwater application. When we talk about the underwater photovoltaic, you need to think about the shear force for the ocean waves because very strong and very powerful. So only flexible device can be alive in the ocean. So underwater, so the solar spectrum change a lot from the gray color like this, so to the yellow color one. So under 1 meter under water surface, and which means we need to tune the material to match the spectrum like this. And so we designed the material like this one, and realize quite good efficiency for this condition. So we make the flexible solar cell and realize about a 20% efficiency on the water for the 1 meter water, and for this device. And for the rigid one, so it's very easy to realize. 25% efficiency, and it should be emphasized that for underwater application, the temperature control is very easy. So the stability for this application for the OPV is quite good. And after 1,000 hours, efficiency changes a little bit. And the last one is, let's think about a little bit more to print an OPV cell under a regular surface, like like here, like over there, something. So if you have a surface, have a regular surface, which means you cannot use the blade coating or the other type of coating technology. So deep coating is quite good for this one. So in this paper, we reported this. So by tuning the coating speed and also the viscosity of the solution and the composition of the solution, we can tune the morphology something like this. So within the different direction, you get a different surface morphology and the aggregation morphology in the film. And after this, so we realize about a 18% efficiency for the best condition. So for that one is very similar to the spin coating device. So deep coating is, for the rigid cell, deep coating is not so easy to realize. If you have this size device, it's very difficult to make something to container to coat. However, for the flexible device, it's very easy. So you just need a roll like this and to coat a very long device. And also you can coat the OPV device onto a copper rod or metal rod. So you need to make the copper rod very shiny, clean it, and then dip the rod into the P dot solution and out, and then active layer, and then like a silver nano wire something like this, and then you get a device like this, and which means let's see the efficiency for the rigid one. So it's very easy to realize. Quite a good efficiency for the flexible one. So for this dimension, like 10 centimeter plus 1 centimeter in width, and like this is a 14% efficiency something on the road. So it's very difficult to calculate the efficiency, but the device works. So at the last, I would like to make a look. So for PCE, we're still looking for a new material to generate a very high efficiency. Maybe 24% efficiency. And for the cost, I think, so P3T PCBM will be a very good benchmark because that one. So for you just need to use $1 or $2 to coat one square meter area. So the material cost is very good. And for the lifetime, right now the OPV device is quite easy to realize 5 to 10 years lifetime right now. And the last one, the most important, we need to think about unique features and more functions for OPV. And after that, OPV can get a very good success. At the last, I would like to thank our collaborator, like Professor Feng. They help us a lot for the mechanical study. And Professor Ye Long, Professor Hao Xiaotao, Zhang Maojie, Professor Wu Hanyong, and Professor Wei Zhixiang, Professor Ma Wei, Professor Peng Jing, and also financial support from the government. And thank you.
Questions, comments? I saw you first.
So thank you. So I have an advantage because I'm right in front of you. Right? Very good summary. The MOC you mentioned, the KAUST MOC. So MOC is like in photovoltaics we call it BOM, bill of materials. That's the material costs, right?
Yes.
So you had the numbers like $20 per gram for D18 Y6, and I can remember 20 years ago when we had E2HD PCBM at the kilogram scale. The cheapest P2HD we were purchasing was at $20 per gram, and PCBM was 35. So how do you get PM6 or Y6 down to $20 per gram?
You mean this one?
Yes. Yeah.
This one?
Any of these? I mean, these are fantastic low numbers.
Because I'm a chemist, I have a combo. I can calculate the material cost very, practically. So it's a real number. So if you trace back to the, kilogram scale raw material,
Okay, so at a kilogram, I can purchase this from your company. Okay, send me the code.
Not a calculator for the labor, right?
Yeah,
For
okay.
labor, yeah.
Yeah, okay, thank you.
Carl?
I don't want to purchase anything. Thanks for the very nice talk. I was impressed by the indoor efficiency, and especially the fill factors went up a lot. Is that simply a series resistance of the module, or is that also recombination?
Recommendation, I think.
Yeah.
I mean, the defect in the material, I think, and the interface for that one, very important. And also for the indoor application, especially for the very weak intensity light intensity, the defects in the material should be, controlled very strictly.
I see a question there, David.
Can you give someone who's not an organic chemist some idea of what you mean by a short synthetic route? Is it one step from a bulk chemical that I can buy for a few dollars per kilogram or less? Or
Yes.
5 or 10?
How to define short?
Yes.
Synthetic steps, right? I don't know how to use my language to with you. From my understanding, it's very easy to find. The large scale material from chemical books, right? Yeah, but you can also customize your monomer from some special company. But you cannot do that to do the calculation.
Did I see yet another question? Paul?
So for your large area devices, do you use a metal grid for the current collection, or because you have these large area devices?
Yes.
Do you then use a metal grid for the current collection? So P dot alone is not sufficient in conductivity.
Oh, you mean for the indoor application, that one?
Yeah, the big
because for the
devices
indoor
that you
application,
showed.
the series resistance is not so sensitive. Because the current density in the device is very low. So, so even if you, use low resistance, high resistance, high sheet resistance ITO, you still get a very good fill factor. Yeah.
We have one question from the audience here.
Yeah, so I'm curious about the deep coating. So when you dip the copper into the solution, when you dip it, it could be some drops in the bottom. How do you deal with it? Because it can cause, if you don't deal with it, it can cause over aggregation or something.
Okay, we only use the middle part of the rod to calculate it. Yeah. The other part, you just need to use a solvent to whip out.
So I have further questions from the audience. Then we have a request from the organizers. We should organize a group photo.
Hi, and welcome back to the session after the lunch. This session is going to be focused on organic photovoltaics, and we have a lineup of speakers. The very first speaker will be online, Derya Baran from KAUST, King Abdullah Institute for Science and Technology. She has unfortunately not been able to travel, but we're very happy to have you here, Derya, for this lecture online. So the title, as you can see, Resilient and Sustainable Organic Semiconductors. Welcome, Derya, please, the floor is yours.
Hi, everyone. Am I audible?
Really?
Okay, fantastic. It's such a pity that I'm not here, and I can't also see any of you, unfortunately. But I hope you're all doing well and enjoying fika time in Sweden on maybe a sunny day. I will show you if it is sunny or not in a second, actually live. So today I'd like to dive into my talk I was thinking to do a usual talk as we always do on organic photovoltaics and semiconductors, and I will show you some of my work. But I also have some surprises at the end of my talk that how we can make some materials impact towards sustainability on the bigger picture. So, in one of our recent perspectives this year, we focused on the growing demand of organic photovoltaic materials and devices, and obviously the growing published papers, and the reasons that there are great reasons like why. Sorry, I'm trying to find my spotlight here. The reasons that why there's this growing demand towards organic photovoltaic materials and devices because of their several advantages and their applications. So there are several aspects to cover in terms of sustainability, which I hope some of the speakers touched upon in the previous talks. And today I will mainly show you the material processability and the stability towards efficiency and how it impacts the applications, obviously, in terms of devices. And if you would like to read more in depth, you can have a look on this perspective. I'm just seeing that if I use in Zoom, I can't use my laser and slides. So sorry if it's slow transitions. Okay, so in this talk, I would like to focus on the three aspects. As I said, the first, the sustainability of materials, and the stability part as a second. And if I have time, I would like to show you how we utilize some of these organic semiconductors for impact in the global scale. The first study I would like to share with you is published a couple of years back when we were looking for actually the printing organic photovoltaic devices. And my student Daniel and Diego back then were very environmentally conscious two students, with what they eat, what they do, what they wear, where they go in their world. They really wanted to do something different with organic photovoltaics as well towards sustainability. So here you see the brief chart for these organic photovoltaics in terms of their benefits, for instance, in toxicity and recycling and integrability towards IoT and other devices, as well as many other factors exist in other photovoltaic devices, which is combined with the R&D efforts towards scaling and upscaling. I'm sure you're all familiar with these steps where we start from glove box processes and use spin coating techniques in small areas of materials. And obviously, towards scaling up and commercialization, there is need for modules and move from evaporated devices to the printed devices, as well as green solvents. I think in a couple of years back in one of my talks, I said I'm really sad to see that this green processing is at the end of this scaling up, but I also totally understand the efforts that goes along with the efficiency and stability towards it. But I will show you what we have done in this space a couple of years back. So we want to say, okay, in organic solar cells should be green and sustainable. However, when we look at the solvents that we're using most of the time to achieve the high performances in these devices are toxic and unsustainable. Mostly you will come up with the solvent names, chlorbenzenes, dichlorobenzene, even some of the toluene. Nowadays, maybe new solvents such as xylene getting better, as you also see some of the green solvents such as limonene and so on are being tried. However, there is this trade-off between where you're going towards greener and greener solvents that you sacrifice from your power conversion efficiencies. For instance, ideally using alcohols or ketones or even water, the performances of these solar cells were decreasing. So we did a brief analysis on the global warming potential of these solvents beyond that they are unsustainable. And if we want to use them in the printed solar cells, they're actually quite high kilogram CO2 equivalent if you would like to print them in the large scales and in ambient environments. And the obvious picture is if you move away from these solvents and go to, for instance, toluene or benzene or xylenes, you can decrease this global warming potential. So we wanted to understand this solvent interaction with the organic semiconductors from a miscibility perspective, and we used Hansen solubility parameter framework to build actually a framework that how the materials interact with the solvents, and how can we find a sustainable and green solvent that also works efficiently and stable. So as many of you would recall that actually Hansen solubility parameters framework based on the dispersive polar and hydrogen bonding of materials, and you create a HSB distance which describes you the likeness of the solvent and the material, where you're drawing try to get this where you're drawing a solubility sphere here, and you identify certain solvents, and if they're outside of your sphere, depending on how you define this sphere, if they're outside of your sphere, then you say they're not soluble, and if they're inside, you say define them as soluble. So what this framework helps you is actually identifying the alternative solvents, as well as formulation guidelines where you can actually look, especially in bulk heterojunctions, where a donor and an acceptor exist. How can I adjust this likeliness of these solvents towards the solubility, and I can print them, obviously. So after several iterations and optimizations, we have identified several terpene-based renewable solvents for organic photovoltaics. As you see here, depending on their boiling point and the oral toxicity, we identified, for instance, eucalyptol or pinene materials. They are as bad or as good as baking soda, for instance, or as fructose compared to the chloroform and chlorobenzene solvents that we are using. And when we go back to the global warming potential picture again, where we can make these terpene materials, where we can make these terpene materials via distillation using biopolymers, then we have actually seen that you can significantly reduce this GWP if you consider this CO2 valorization and use some of the CO2 through actually even here in the biorefinery processing methods, and then we utilize them back to feed them back to organic electronics, then you can actually even achieve a negative global warming potential. So this initial calculations were very exciting to us, because not only the solvents that you can use from nature, for instance, exists in many different ways. You can not only get solvents, but also some of the building blocks of the organic semiconductors, which we didn't look into, but it was so exciting to dive into this area as well in order to create this cyclic processes. So then after we came up with this terpene solvents, we wanted to explore how they will contribute to the drying kinetics of a organic semiconductor layer for OPV, because we wanted it to replicate, for instance, a chloroform or chlorobenzene system in these green solvent systems. And we defined a solvent affinity, as you see here, where we consider these the RA, the radius, as I told you earlier, towards the donor and acceptor with these solvents, and we identified the solubility parameter if they were more akin to the donor material, in this case PM6, or for instance towards the acceptor molecule, EC9 in this case. So we look to different boiling points and different sort of green level solvents here, and from the TGA, as you see here, we looked for their TGA, the evaporation rates, and how they would behave if we combine them in this binary solvent combinations, if they are obeying Rolle's law or deviating from that. And why this was important, because if you look to this right graphs where these drying kinetics seen by, for instance, chloroform DIO system, which is the unsustainable version, how a donor and acceptor, in this case solid and dashed lines, would dry similarly to each other, we wanted to replicate the same thing with the other greener terpene family solvents by varying their boiling points and their affinity towards the donor and acceptor molecule. And as you see here, eucalyptol tetraline system was very similar to the chloroform DIO system. And when we look to the Hansen solubility space kinetic drying behaviors, we explained this in our paper that where you mix the donor and acceptor in this binary solvents. And the first is actually a low boiling point solvent is required to dry some of your film that is soluble to the donor material, and it increases the concentration. And once you increase the concentration, then actually the donor saturation point is achieved. And if you then, when you keep actually drying the high boiling point solvent here, then you'll reach the NFA saturation point as a second step, which would give you a similar drying kinetics as this chloroform DIO. So the implications of this terpene solvents after several characterization was reflected in the OPV devices. As you see here, we use several state-of-the-art materials back then. Also, the large area utilized P2HDID TBR all the way to PM6 systems, and we were able to achieve the comparable results where we can have from the chloroform or chlorobenzene systems and up to actually 16% efficiency, which was very, very exciting to us back then. So as a natural step forward, we made OPV modules from these devices, and we took them to outdoor to see how they would survive in a Saudi environment. And with this, actually, we moved all the way from these red lines or red bars to sort of green bars with these green solvents, which was very, very exciting. And then once you are sorted on the solubility, obvious question to my research group over the years has been the stability. And we looked to the Y series that is actually the state-of-the-art acceptor material. So I'll summarize a couple of the stability results we have obtained over the years. As one of them, we looked at several different Y materials with subtle differences either in their peripheral groups or their alkyl chains and shorter or longer. And what we ended up is if you have a fluorine end group compared to a chlorine in this Y series, you could increase the photostability of your devices. And also this was related to the TG of the materials, obviously, in terms of its thermal behavior. So we compared the indoor and outdoor stability of these various different Y systems, and we have shown that the F end group Y12 was one of the best among the others, surviving also the Saudi environment, as you see here on actually my rooftop a couple of years back. So then we wanted to understand the donor stability in the same perspective. Here we looked at several different donor systems with Y6 acceptor, and we tracked the stability trends here. And as you see, PM6, which is one of the state-of-the-art donor material, is not as good as in this case D18 or PC10, mainly because of the light-induced trap-assisted recombination, which exist in several systems. So we were actually looking for the systems that will not show this. And in this paper, we looked to several different parameters, like how we can actually reduce this light-induced trap-assisted recombination with the chemical fine-tuning. And what we ended up is we looked again to outdoor testing of these three devices. And very interestingly, this PC10 Y12 system, Y6 system, survived the most compared to PM6 Y6 in this case. And also the thermal stability was quite nice in the 65 degrees environment here. And when we put them outside again in the Saudi quite harsh conditions, the PC10 Y6 cells were impressive after 7 months of outdoor working. That gives a very promising result towards, again, scale up and the commercialization efforts in this case. So again, you can look from the paper, but it was not only these three systems. We looked to various systems for several different ways of stability in the ISO's O2 conditions. And we explained actually whys and the reasons, like how these sort of lower stability systems can be improved in each group. And you will be realizing several donor and acceptor systems are existing here, including either a polymer small molecule or polymer systems, or even I think some of them are small molecule systems that you can look into. So once we nailed on the photostability, and we understood actually we need to use this device guidelines or material design guidelines, how we can get the high photostability. Obviously, the next question is how about the thermal stability? And over the years, then one of my postdoc, Jianhui, who is a faculty at the moment in Dalian University, came up with this amazing concept of thermostats, which has been known from industry, obviously, and used for several other reasons. However, embedding them into an organic photovoltaic solution or organic semiconductor solution was very difficult and limited simply because of their curing temperatures and also the solubility, miscibility relationships between each other. So after a long search, we have identified some of the cross-linking thermoset matrices here, where we can create based on the hydrogen bonding. And as you see, there are lots of different ways of making thermosets. We thought that we could create a high modulus system. And this high modulus system would give us actually a thermally stable and locked in morphology. And for this reason, we chose this D18Y12 system and many others later on, where we again limited in the end our thermoset matrices to either here EPY and MDA based on this hydrogen bonding interactions. And we compared the this polyaryl ether and the other sort of low modulus systems to see how the thermal behavior will be once we embed them into the organic photovoltaic semiconductors. So in this slide, you're seeing the differential scanning calorimetry and DMTA mechanical analysis to show that we were able to make the thermosets, first of all, the matrix embedded in the bulk heterojunction, and also this system was allowing us to suppress the chain relaxations here, which means that they will be less likely to move. And again, when we look to expanded this concept to several different systems, we have seen that they're working not only similar and in some cases improved power conversion efficiency, as you see here from several different cases. The orange ones show the no thermoset efficiency, and sort of the green ones, if you can see clearly, are with thermoset power conversion efficiency. They are either same or improved in many conditions. But if you looked at the lifetime, thermal stability lifetime, there was a huge improvement compared to, again, no thermoset versus the thermoset in terms of 85 degrees here. I would like to emphasize thermal stability. So this was, again, very motivating and exciting for us. Simply, we live in Saudi Arabia and hot climates to put these materials to outdoors. And when we look at their outdoors performances, the photostability and the thermal stability were significantly improved with interface engineering as well, I have to say here, to almost a stable, actually, trend, which was fantastic to observe. So I think in this specific study, we did almost June, July, over 3 months of study, and July is, you can say, is pretty hot in Saudi environments. So now I want to actually step back to show you, saying, like, I kept saying we did outdoor stability and so on. I would like to show you how we actually did that, because we did several different devices, and it took our years and years and many PhDs and postdocs to actually come to this level. I would like to introduce you our outdoor measurement and hardware and software very briefly. So when we had to do, measurements with Keithley, my postdoc back then, Joel, was saying, it's a bit of a waste of resources and money to measure the solar cell stability with the Keithley. And we were like, can we actually design something smaller so that we can just take our hardware outside? Because it's not only solar cells not surviving in Saudi, but also hardware is quite tough environment. So that's when actually he seeded the first designs of this micro SMU we developed in our group, which was good enough to measure an OPV device, and also cost-wise very, very effective. And once he moved out of KAUST and moved to Swansea, I think he was also clever enough to started his own company Logic, where today you can find some of these SMUs to measure various different organic electronics or other even batteries, different type of devices, which was fantastic. Then, of course, this was not enough to do a whole stability setup. We wanted to design a modular setup that would allow us to measure several different OPV devices. And again, several students worked on it, combining all the today's technologies, I would say, and also the remote possibility of measuring. We designed this gloss system to do our outdoor stability tests. And this, I would say a hobby where we wanted to do a hardware first and then design all the software. We were like, can we put all these things in one box? Can we make it lightweight? Can we put more and more cells and so on? Turned into an incredible global stability study, which was my dream to actually make it over the years. And it came through, if I'm not mistaken, 18th of April this year. And some of the partners, I hope, are in the audience today. At least I know Ellen. I think Quinn had a talk this morning, if I'm not mistaken. And there are two more surprise names that will come actually when we start to measure the devices, simply because they are stuck in customs and global conflicts and everything, let them not move forward. But we are there. So what I want to say is, since a couple of weeks, we started to get our data in Saudi, Sweden, and USA, and thanks to all these people involved. And I think coming back, I was saying, I hope it's a sunny day today in Stockholm, looking to our live data from KAUST, where we can track our OPV devices. I can tell you it's not. Correct me if I'm wrong. And it's very nice and sweet that we can see some of the days here. For instance, the difference between, and this is just a power output. We just got this data quickly that, on a hot sunny Saudi day, you can see the power output versus a cloudy Sweden day. Or I also have to say, a very Nordic, I would say, even when they are very sunny together, a bit of a Nordic different, solar angle versus a much more straight, obviously equatorial positioning of Saudi. You can also see this subtleties on various different OPV devices. I can't give you more detail, unfortunately, now, but I hope very soon we will see how these trends are, and I'll be happy to share with you. So I hope I still have a little bit of time. I just want to show you then from all this, studies, understanding the stability and so on, we were, as you can imagine, very excited, believing in OPV and what we want to do with it. And we said, hey, we can actually move from lab to fab maybe and show some demonstrations that we can apply these OPVs in again, Saudi in the hot climates, because I was excited that we can generate electricity. And simply with this new material design in the infrared region, we were thinking we can use them in the greenhouse applications because we can tailor the light entering towards this chlorophyll production and useful for plants and so on and so forth. So over the years, we moved from this lab scale modules to slightly largely printed prototypes, and with some incubator accelerator programs at KAUST when we were young, I would say, we moved to scaling up these OPV devices. And at the end, maybe one of the first of its kind in this semi-transparent new generation OPV devices were scaled up to 200 square meter pilots in the greenhouse here at KAUST. So here you can see some of the pictures. Actually, I will have to admit that installing these modules were harder than making them and scaling them up. It's a bit oversight, I would say. But we made it, and we grew actually lettuces, strawberries, and tomatoes under them. And also there will be some sort of stories coming up how the outcomes were with this installation of the OPV. But I want to take the last sort of, I think, 5 to 10 minutes shifting a bit your focus, because coming back to this last slide, okay, my main research on organic semiconductors, and we claim they are sort of direct oil components and they can be synthetically available, or that would help, geographical diversification of the raw materials maybe in one day. They are all good. But we focus solely on electricity generation in this OPV devices, and I did this so far as well. But living in Saudi helped me to shift my perspective, because we were working with plant scientists in this project, and we were telling them, what, you have, like you can generate electricity where you can block some of the infrared light in this. And then they told us, well, you can block infrared light, and saying yes. So, but with that, you can also reduce the temperature. And we were saying, yeah, as a side, you can reduce the temperature. However, it was until that moment we didn't even perceive how big issue this hot temperatures and cooling in Saudi and hot climates globally at the time. So again, as I said, it's not only in Saudi, but there's also California, Spain, Egypt, Mexico, Europe, and you'll be surprised, even UK, as you see here with the global warming, suffer from these hot temperatures that results in water scarcity, but also grow food at risk. So I think we should start looking to this energy issue not from a singular perspective, but it's actually a nexus of this energy, water, food nexus, which has been recognized in some of these platforms. So obviously, United Nations and SDG goals also recognize this. And when you read this sustainable development, you see agriculture is the largest consumer of the world's freshwater resources. And water is used to produce most of the forms of energy. So you might not collect and click this, because in Sweden or Netherlands or most of the Nordic countries, a greenhouse requires actually heating, in order to perform at its maximum. However, in the hot climates or equatorial environments, you need a lot of cooling, and this cooling of the green covered agriculture is coming from using, you'll be surprised, fresh water, and is really, really unsustainable. So actually anything that you could work for towards reducing this use of this fresh water, or reduce the temperatures of this covered agriculture for better plant growth, would be highly impactful. I don't think I need to convince this environment that there's a huge infrared portion of the solar spectrum. This is a bit of an underrated slide, but I can tell you at least this infrared or near infrared, even the part of the solar spectrum, is very bad for plant growth. And if you talk to plant scientists, they would say like this 730 nanometer is very bad for fruiting, and 750 is even worse for instance, pollination, UV sites, etc. So it's very, very sensitive in terms of large scale production. And what we did with this perspective of actually requirement for cooling and resource use, we designed a passive cooling technology and shifted our startup company to focus on the reduced solar load in protected agriculture for the hot climate. So it's actually a very simple context to this audience again, is when you cover your greenhouse roof with these certain materials, you actually reduce the load of the infrared light and allow what plants like and sort of block what plants would not like. And what we did in this case is our initial tests showed that actually our second sky product blocked majority of the infrared transmission, and we actually proved this with the third party manufacturer lab tests, which gave us more confidence that we could consider maybe a scale up in this perspective. And I have to say, what the scale up means in this case was actually much easier compared to whole OPV scale up to a gigawatt scale, I would say, but it still had its challenges. But what I can tell you is we managed to, in this case, embed certain materials into one of the world's sort of cheapest agriculture material, and also scale this up to put it in the greenhouse roofs. So why this is important? Because we were focusing on the greatest impact, and also a compatible product that is used in the 90% of the covered agriculture. And if you look, for instance, to subarctic temperatures, where the protected agriculture is still a huge area. But if you move to the Mediterranean and subtropical, is actually almost 10 times more area required to cool down, I would say. And then we applied this to scale up to the shade nets or polycarbonate or polyethylene type of products, which are widely used in greenhouse market, I would say. So then obviously the first experiments started in our KAUST research labs, where we grew a lettuce, I would say proudly, as material scientists and chemists, thinking that, wow, we did a huge achievement, you know. And then what we proven here was where we were doing, maybe you see a bit slightly bluish coverage here versus actually just a greenhouse film. We tracked the temperature required to cool down, so the energy required to cool down these two small greenhouse boxes, and shown that this concept works, and all the way to a scalable material where you see the second sky product here in a covered greenhouse. If I'm not mistaken, this is in Spain. So with this scale up, we put our products, I would say, to several places to deliver real benefits to farmers and in harsh conditions. For instance, what this greenhouse film does is, for instance, in Almeria, Spain, you see a huge area of greenhouse, I would say, alley, where we can do the temperature reduction at the peak reduction, which helps obviously to grow plants better. Or in Riyadh, Saudi Arabia, we obviously have water use reduction, which is quite significant, where actually all the water is desalinated in the country. Or in Arizona states in US, you can also increase the yield because it's a very similar environment here. So depending on where these greenhouses are, you could have one or combined benefits of all these things to reduce the resource use and increase the sustainability. And in the end, we thought, okay, actually this polyethylene film is not very sustainable itself, and it's only single use. We took the liberty to launch the world's first, actually, this is like an international sustainable standardization certificate film, working with SABIC here, a product called True Circle. We embedded our materials into this to make the fully sustainable and non-petroleum based products, and actually apply it to a large area greenhouse in the north sides of Saudi Arabia that is delivering fully sustainable food to the region. And in terms of startup ideas, obviously we extended this for the end of use responsibility and duty of care, considering recycling and reprocessing and all this as well. So sorry, I actually moved a little bit outside the topic, but I hope at least I was aligned with the sustainability aspect of these things, and show you how semiconductor materials and organic semiconductors are very exciting avenue, and it's growing and growing globally. And there are more than one way to actually look at these materials to make them more sustainable and contribute to hopefully a better world. So with that, I would like to thank you for your attention, and I will be happy to have questions if there are any.
Thank you very much, Derya. Questions for Derya? It's okay, she will hear you when you ask a question. So
yes, I couldn't even hear my...
There's so far nobody raising a hand, but yes, please.
Hi, really nice to talk with you. It's Jessica. I don't know if you remember me, but I'm working with Bella on the...
yes. Hi, Jessica.
Hi, really nice to see you. I had a question actually about the terpenes paper. This is a really interesting paper for me, and I have actually based a master's project on this. This is my master's student. I don't know if you can see her, but she's next to me.
Fantastic.
But something we've observed with the terpenes is that they're kind of quite reactive to like oxygen, heat, light, things like that. And we had some complications for a while where we were finding they were forming like non-volatile isomers that can get like it can lead to residual solvent getting stuck in the inks and stuff like that. And I was wondering if you guys also had some kind of complications like that, or.
It's very interesting. I don't know at which stage. Sorry, maybe two microphones are open at the same time. I don't know at which stage of your processing you mentioned this, but we actually did even print these devices, print these inks, so to say, in air. And especially with eucalyptal system, we haven't observed any of those complications you mentioned. However, I also have to admit we didn't follow up further on looking, the ink stability or the reactions. So, for instance, we didn't put the ink to a harsh temperature conditions to look for what is happening and so on. I think if you would like to do that, I believe you can definitely find some other things going on. However, what I know, I can tell you from other conferences I showed this, and I know other people reproduced results and use these solvent combinations effectively. But I would be happy to talk separately about this, at which part you have observed these things, under which certain circumstances. That's what I feel.
Of course. Thank you.
Thank you. Anna Köhler.
Hi, Derya. Really, really nice talk. I have one question. When you actually put your organic solar cell on your foil as a greenhouse cover, at which rates do you think you need to replace them now and say in a few years' time when the development has progressed? Is it something that you have to replace yearly or in shorter term periods or in longer ones?
Yeah, so I have to be honest that those films did not live too long, but I have to say it was not because of the organic OPV layer at least. I think there are several issues that we can touch on the module level. It was mainly because of the encapsulation layers and the lamination. So if we know that it works perfectly, as in our outdoor stability measurements, for instance, I can tell you at least they would survive very well 7 months without any, and we measure obviously all the time. And it's quite a harsh condition under VOC conditions for this OPV. But when you make module and put it on a rooftop and so on, there are a lot of other intertwined issues come into play. And in this case, as I said, encapsulation and the lamination was the bottleneck rather than the OPV itself, if it explains. But what you would want ideally, I know, is it's just a cost balance of systems, cost balance. Like it depends how much you spend for the OPV module would pay back, and you ideally would like to keep it as long as that time. And it was 5 to 7 years, if I'm not mistaken, when we did the calculation for a greenhouse. And as usual greenhouse film is replaced every 2 to 3 years, polyethylene.
I need to close the discussion here. Thank you very much, Derya. You get a big applause here from the distance.
Thank you very much. It's all good to see some of you. And I hope to see you in another occasion. Have a great symposium.
Bye. And we're moving on to Jenny Nelson's talk. Jenny is from Imperial College in London and is going to talk to us about modeling solar energy conversion in molecular electronic materials. The floor is yours, Jenny. Coming up. It's coming up.
So thank you very much to Ellen, Feng, Tunu, and Ole for the invitation, Peter for all of the organization, and everybody for coming and listening. It's a fantastic symposium. So, as Ellen says, I'm going to talk about what we need to do to try to model the performance of solar cells and potentially other devices made from molecular electronic materials. And I'll start with a few sort of remarks on what we think we know and what we've learned about the function of organic solar energy conversion systems over the last couple of decades, or more in fact. The first thing I think that's fairly commonly accepted is that we need a heterojunction to split the photogenerated exciton and get charges. Having got this heterojunction, that then introduces a compromise between photocurrent and photovoltage generation. We also know that our voltage is relatively unimpressive compared to some other material systems given the band gap, and that's attributed to a relatively high rate of non-radiative recombination. And then what controls the sort of power conversion at operating point, the fill factor, will be strongly related to the onward transfer from so I need to figure out how to do this. I was afraid of pointing at somebody. The onward transfer from this critical sort of interfacial charge transfer state on to charge separated states. And as we know from previous talks and generally, the performance of organic solar cells has improved remarkably, persistently over these years. And we've seen most of the improvements in performance have come about because of new materials. First of all, the introduction of new donor polymers. Then more recently, to some people's surprise, the introduction of molecular acceptor materials. And then most recently, the performance improvements are coming not so much from completely new generations of materials, but rather from modulations in the microstructure and the way existing high-performance materials are packed. And that's led us to efficiencies over 20% nowadays. As Richard commented earlier, 20% used to be a good number, but it's not anymore. And if we look in particular at where OPVs, and they're represented here in pink, underperform, we can see that they underperform particularly, sorry, getting my laser back. Sorry. I'm quite got the screen. I'm used to pointing.
That only works when you, change the slide.
Only works when I change the slide, okay.
You
can see that the, I won't try anymore.
Press and hold.
Press and hold. Huh?
Yeah, it should.
Oh.
Maybe it's try on the just
change the slide.
if there are.
I'm always afraid of pointing these things at people. We can get by, it's fine. Okay, so we can see that they underperform, particularly in terms of, compared to other classes of materials, particularly in terms of open circuit voltage, and to some extent also in terms of fill factor. And so if we would like to understand, first of all, what limits performance, and secondly, what potential there is to find materials with improved performance, we need some kind of modeling framework to connect the chemistry ultimately to the performance of the device. And traditionally, there are really two ways that that's been done. And one way, very common in our field, is to look at it in terms of transitions between different molecular states and to use sort of formalisms from physical chemistry to describe the rates of those transitions. And that has the advantage that you can relate those rates directly to the properties of the materials through calculations of the electronic structure and so on. It has a disadvantage that it's not really representing a device, and it can't tell you anything about transport, about electrodes, and so on. On the other hand, if you use a semiconductor device model, that will allow you to treat the device well, but it gives you no capability to connect the sort of effective medium parameters that you must put into this model to the properties of those molecules that you start with. That would be another step of abstraction which will take you further away from the materials. And actually neither of these approaches is very good at treating microstructure. So what we're going to do is then to look at a variety of questions and see what level of modelling do we need to try to understand it. And I'm going to start with this problem of why the voltage is so low, why is non-radiative recombination high in OPVs. So in our devices, we expect that the recombination should occur at the interface where the electron and hole come together through the decay of whatever state they form at that interface. We'll call it a charge transfer state. And any solar cell device has got a limit to the open circuit voltage that it can generate. In the ideal limit, that's when all the only recombination is the unavoidable radiative recombination that must occur. And that radiative open circuit voltage is something that you can actually work out from the device if you measure its electroluminescence and compare that with its quantum efficiency. So that's something that can be done. And then having done that, you can compare that with the open circuit voltage it really gives you. And then you have a difference, which is a sort of the voltage equivalent of the deviation from ideality of that solar cell. It's sort of it's a measure of its radiative efficiency or its radiative inefficiency. We call that the delta VOC NR. And when we look at the data for organic solar cells, they're represented by the blue symbols in the figure above. They tend to be relatively large. When expressed as a voltage, they may be at least 0.2 eV. Some of the best systems are a little bit smaller than that now. But nevertheless, those are large numbers, and therefore they're large losses in comparison with the best of other classes of solar cells. We can always pick out gallium arsenide as the winner in everything, but perovskites are doing pretty well, and silicon is not bad. So here we have a limitation, and then the question is, can we rationalize that, and how could we do better? So actually, the phenomenon is represented not too badly if we just consider the rate of radiative and non-radiative recombination from a charge transfer state that's formed between the donor and acceptor and the ground state of that system. We can use semi-classical theories, like here we use Marcus Lewis-Jortner theory to calculate the rate of non-radiative decay and the rate of radiative decay. And those expressions involve parameters that we can calculate from the molecular structure, like the reorganization energy, the oscillator strength of the CT strength, the energy of the state, of course, and so on. So in the end, we can end up with an expression for this non-radiative loss, which is in terms of things, quantities that you should be able to calculate, maybe not very accurately, but nevertheless you have access to them through the chemical structure. So with this formula, we can then look at, okay, what could we change? How would this non-radiative loss depend on these different parameters? Oh, got it. No.
It's gone.
It's gone, never mind. It's transient. What could we do if everything else was constant to try to reduce the non-radiative loss? One thing, and it won't be surprising, is that if we can reduce the reorganization energy, here we've expressed it in terms of the inner and the outer terms, but basically this is talking about the same phenomenon that Richard spoke about earlier, which is the electronic the coupling between the electronic states of our system, excited states of our system, and the relatively high energy vibrational modes of the system. Another thing that we can do is, if we can increase the oscillator strength of the donor-acceptor complex, that will tend to reduce the non-radiative losses. And fairly obviously, if we can increase the energy of the CT state, that would reduce the losses. So that gives us some clue about where we could go. And when we did this work, we also generated a sort of projection of what the limiting efficiency might be. There's two things wrong with that. One, it was too pessimistic. And the second one is that it doesn't include one of the most important things, which I'll move on to next, which is how to treat the efficiency of current generation when your offset becomes small. So this is the next question. And here, if we say now we know, we want to have a high open circuit voltage, of course. The high open circuit voltage is directly linked to the energy of this interfacial state. So if you have any given pair of materials and if you have some freedom over their molecular orbital energies, then you might want to move them as close as possible in order to have the highest possible energy CT state and therefore the highest possible voltage. And that would be a sensible thing to do, except when you do it, you find that the photocurrent generation becomes limited. These are data from Frederick Lacaille when he was in KAUST, showing that the internal quantum efficiency becomes compromised when this offset, and he measures it in terms of the difference in ionization energy of donor and acceptor, becomes less than about 0.4 electron volts. So that is a compromise, and now if we want to understand how low can we go with this offset, we need a model which is able to take into account not only recombination, but also charge transfer processes between our excited state, our charge transfer excited state, and the charge separated states that would connect to the external circuit. And so the way that we dealt with this was to take a sort of an interfacial rate model and then integrate it into a device model and directly couple this sort of charge transfer state to the electrons and holes in the device model, and by representing the charge separated state in terms of electron and hole. And then we have a sort of a model which actually is quite powerful, but it depends on many parameters. And if all we want to do is produce a current voltage curve, then of course it will be very hard to find a unique solution. So when we have a model with many parameters, if we want to really use it and test it, we need to have a lot of experimental data. And in this study, then we found that when we combined different types of experimental data and then used this model to reproduce those data, then we could get a reasonably good handle on different parameters which were important in controlling performance. So for example, with our sort of steady state spectroscopy, photoluminescence, electroluminescence, quantum efficiency, we have that data, we have transient spectroscopy, we have transient optoelectronic measurements, and we feed them into the model, and then with the model we simultaneously try to fit all of those, and then that could come out for this set of material systems that we looked at with sort of relatively well-constrained values for different parameters that come into the model, like the energies of the charge transfer state, reorganization energies, oscillator strengths, and the rates of transfer between the different states in the system. And then once you have that, then you could model the current voltage curves, and we find that when the offset is low, then although our voltage is indeed increased as you would expect it to be, we find that the fill factor and the short circuit current density are compromised, which is what happens in practice. So this then gives us a tool with which we could then explore what might be possible if we were to change some of the parameters. Now, one thing I should say here, if we ask what's going on in a low offset system, so when our difference in the ionization energies becomes small, then the energy gap between the local exciton and the charge transfer state becomes small. The gap between the charge transfer state and the charge separated state also becomes small. And so both of the backward processes, both the combination of separate electrons and holes to repopulate the charge transfer state, and that state is quite lossy, so recombination occurs quite fast to ground. From there, that will accelerate, and also the reformation of the exciton will also accelerate, and we begin to get more emission from the excitonic state. And then that means it matters, actually, what about the lifetime of the excitonic state? So a longer lifetime excitonic state will perform better than a lower lifetime excitonic state in a model like this. We can also then sort of calculate some projection of a limit to efficiency. Of course, it will depend on the parameters that we use, but here is a sort of an example where the black line represents the Shockley-Queisser limit and the green line represents the limit that would come out of this model. This is in the case of having a relatively small reorganization energy for the exciton, and we can see that there's a very different behavior, and the failure of the system to perform well at low offsets is because these back processes are accelerating as that offset becomes small. And actually we can modulate the position of this upturn by modulating things like the lifetime of the exciton. We can compare this sort of projection with data in the literature, and here are a lot of points representing devices that have been reported in the literature. We see that in terms of the sort of projection of what's possible, this model with the parameters that we've chosen isn't bad. And most of the values that we see on this sort of rising edge of the model projection have come about because of this recent generation of molecular acceptors, which have led to the increase in performance. So for the next part, I would now like to focus on those materials. And within that focus, I'm going to address the question of whether we need a heterojunction at all. So the new acceptors, often called non-fullerene acceptors, we can say what's special about them. Well, there's a wide variety of them. So, of course, there's a wide variety of properties they may have. The ones that perform well tend to be flat, so they pack rather well, relatively crystalline. They have quite promising properties in the excited state. So they're characterized by relatively long exciton lifetimes and relatively long exciton diffusion lengths compared to other organic semiconductors. And if we look at the properties in the solid state, they're often characterized by quite a strong redshift between this is a light absorption in solution and in the solid state. And that's usually a sign of a relatively strong delocalization, relatively strong coupling, relatively strong delocalization of the excited state for the material in solid. So these are things that we will come back to. But when we look at the characteristics of how they behave in heterojunctions, there's 2 points to make. And I mean, one is there are many reports that these heterojunctions made with these non-fullerene acceptors are able to generate photocurrent at a lower offset than traditional materials. So they seem to be able to overcome or at least ameliorate the problem of needing this heterojunction. And also at low offset, they tend to perform with relatively low voltage losses. Now that's actually something you would physically expect, but still the evidence is there. And so those two things together will already give you a higher performance. But then more interestingly, there have been suggestions that maybe the reason solar cell heterojunctions perform so well using these non-fullerene acceptors is because excitons are actually dissociating spontaneously in the acceptor domain themselves. So this is a paper where it was suggested about 5 years ago, and then more recently there's been a suggestion that devices made from the pure acceptor can actually generate photocurrent by themselves without needing a heterojunction, and there's also been theory about that. So that's a question we would like to look at, about whether charge pair generation does occur spontaneously in the new acceptors. And to do that, we started with some experimental work, and we took the decision to look at the performance. They basically a very, very simple concept that we put our organic semiconductor in a device between two blocking electrodes, and they need to be blocking so that there isn't any accidental unintended charge generation at an interface, which could occur if one of your interfaces happened to be presenting a heterojunction. That's what's shown in the blue case. If we avoid it, and then we look at the photocurrent as a function of applied reverse bias electric field, we see this nice sigmoidal behavior where it rises and saturates at some point where virtually all of the excitons are dissociating. And so what's happening here, we can consider when no field is applied, it would be quite unfavorable for a local exciton to then populate the material will in general have charge transfer states. It will have charge separated states, but because of the Coulombic binding energy, those are going to be higher in energy than the local exciton. But when you apply a field, then they become stabilized, and then it becomes energetically favorable for the exciton to dissociate into a charge transfer state or a charge separated state. And this is the phenomenon that we think we're exploring. And here are some data for the case of the non-fullerene acceptor Y5. As we apply the bias, the external quantum efficiency spectrum grows. we can look at that as a function of field. It shows this nice sigmoidal behavior. And the same sigmoidal behavior is actually reflected as well, also by the photoluminescence quenching, which follows the same trend. And if we measure the photoluminescence quenching from the change in lifetime of the exciton, that again shows the same trend. So we seem to have this very nice field modulated competition between photocurrent generation and light emission. That's what happened in the case of Y5, one of the Y family materials, but we can then look at a lot of other materials. So everything that's shown in blue here are the elements or members of the Y family, and there's some differences amongst them, but they all show this sigmoidal behavior. And then we see what happens when we move to another family. So we move to the ITIC and related compounds, family of non-fullerene acceptors, and then we get the data that are represented by the red curve. So we see they do the same thing, but they require a bit more field to stimulate the photocurrent. And then we look at another family of non-fullerene acceptors. We took two IDTBR analogues and looked at those. And again, they show the same sigmoidal behavior, but they require more field to generate the photocurrent. So there seems to be some difference between the material families in terms of how easily they generate photocurrent. And to put it in context, I can also put here the purple line represents a conjugated polymer, it's P3HT, and you can see that they're all better than P3HT, but despite being better than a conjugated polymer, they're not really useful at all in terms of generating significant photocurrent in what would be short circuit conditions in a solar cell. We need to apply a field, and when you apply a field, that's not your photovoltaic regime, but there are differences. So then we can move on to the same materials and look at them in a heterojunction situation. And we decide to try to minimize questions about differences in microstructure. We decide to use a planar heterojunction, and we use a very wide bandgap donor. We use copper thiocyanate so that it's only there to collect the holes and nothing else. And then we make planar heterojunction devices with different acceptors, and by modulating the ionization energy of the acceptor, then we modulate the size of the offset between the donor and acceptor at the heterojunction. So these are the quantum efficiency that we measure. Now, no field applied, just the solar cell, this planar heterojunction at short circuit. And as we change the size of the offset, the quantum efficiency changes. And we can plot that as the internal quantum efficiency against the offset in ionization energies. And we see there's a trend as the offset gets larger, the internal quantum efficiency gets larger. And we can then compare it with the Y family. And the Y family pretty much do the same thing, but they do it earlier. So they're able to generate photocurrent, but and it increases with offset, but they're able to generate more photocurrent than the, or higher internal quantum efficiency than the ITIC series, even at the same offset. So again, we see a difference between the two families of acceptor materials. And then this asks, simply seeing the same behavior, it then sort of raises the question that I was bringing up when I introduced the topic, of whether it's possible that some kind of dissociation in the acceptor domain is actually what is contributing to the better performance of the bilayer when it has Y rather than ITIC acceptor materials. So to look at this, we needed a model. And I've been talking about models like this, where we have an excited state, a charge transfer state, a charge separated state. But now we want to be able to distinguish between different materials, different chemical structures, and this is not easy to do. We need to know a little bit more about the nature of the states. And if we look at the literature about these materials, one thing that's very clear is that the electronic coupling, the packing of the materials is quite strong. The electronic couplings between neighboring molecules, when they've been calculated, they're calculated to be strong. A theory that's been done on the nature of the excited states is telling us they're quite broadened by the excitonic coupling, and they do have significant charge transfer character. So we can't use a model like that. We need to go a little bit beyond it and somehow take account of the different types of excited states that could exist within an assembly of molecules like this. So the elements of our model pretty much are like this. In theory, we start with a structure. It could be a crystal structure that's pulled out of literature, or it could be a lattice, if we're just interested in the question at a kind of toy model. And then that gives us the positions of our sites. So we coarse grain it, so each molecule is a site. And then we have the positions and the energies. And then we build a tight binding Hamiltonian. This is in an electron hole basis, which means the elements of it are both Frenkel excitons and charge transfer excitons, where the electron and the hole may sit on different molecules. And from that basis, then we can build up all of the singly excited states of the system. And this is a sort of the graph here is showing the type of states that we could get. The orange states represent those with local exciton character, where there's no separation between electron and hole. And then we can characterize other states in the system in terms of their degree of charge transfer character. And if it's a lot, we call them charge separated. If it's not so much, we call them charge transfer. Then having got the states, we can then model transitions between the states using a master equation, and then we use what we believe and hope are appropriate rate theories for the rates. And then we can get, for some condition, the populations, let's say, as a function of time, and then we could model experimental data like absorption, emission, charge generation efficiency, etc. So this is kind of the framework. And then we take this framework and we apply it to our to the systems that we've been looking at. First thing, we look at a simple domain of one material when an electric field is applied. When the field is applied, it stabilizes those states with some of the states with greater charge transfer character. And then we can use the model to simulate the charge generation efficiency as a function of field applied. And we look at what are the parameters that go into our model that could help this. The one parameter that would help, and it will surprise nobody, is to reduce the exciton binding energy, okay? And then another parameter that would help would be to increase the electronic coupling between neighboring molecules, and another is to reduce the reorganization energy for the local exciton. So those are three things that would help. In the case of the first experiment, we're looking at photocurrent generation efficiency as a function of field in a single component. We can apply the same model to a heterojunction. And when we do that, then the effect of changing, we're looking now at the effect of changing the offset. And if you increase the offset, then that would modulate the energies of the charge transfer state manifold relative to the local excited states. And when we do that, we actually find the same parameters benefit charge generation. Again, if we have a low exciton binding energy, strong electronic coupling, a low exciton reorganization energy, all of those things would help to turn on charge generation at a lower offset. So the same things that help you in the field help you when you have an offset. And then it takes us back to the, sorry, it should have been, I wanted a question. Anyway, so then we can ask the question, it's here, about whether it is true, now we have the model, we can look and see whether the sort of favorable generation in heterojunction is helped by generation, spontaneous generation in the acceptor domain. And the answer basically was no. The right-hand picture here, I'm looking at charge generation for different exciton binding energies. The blue is a very small one, and then the green, orange are higher values. And there are two sets of data are shown. The crosses are for the generation that happens at the interface, and the circles are for what happens in the acceptor domain itself. And what it's telling us is that normally, except if the exciton binding energy is very, very small, virtually all of the generation is happening at an interface. it's not happening in the acceptor domains themselves. However, the same properties that help in the heterojunction, that help to drive current under field in the acceptor alone, also helps to drive photocurrent at the heterojunction, and that will be because of the greater extent and the lower binding of the charge transfer states that are involved. We can also look at where are the limits? What is limiting our current generation? In the case of the experiment in field, it's almost a direct competition between dissociation of the exciton and generation of charges. So anything that we don't collect is because the exciton wasn't separated. Whereas in the case of the heterojunction, at low offset, it's like that. And at high offset, we get into the regime that I was looking at the beginning of the talk, which is where we're losing power because of non-radiative recombination through the CT state. And with the model, you can, of course, explore this and see what parameters would benefit different areas. If we compare, so we had identified certain parameters that we thought would be a good idea. Is it true that Y6 is better than ITIC? In terms of exciton binding energy, so in literature we would say the jury was out. If people know better, I'm happy to hear it. In terms of electronic coupling, certainly yes. Reports tell us that the electronic coupling in Y6 is better than higher than in ITIC, and also exciton reorganization energy is lower in Y6, therefore better than in ITIC. So, and that's also here some reports of calculations and measurements that support that. We also have some of our own that support the idea that the exciton binding energy is significantly lower in the Y family than in other families. This is now moving on to something which is not yet complete. But when I started at the beginning, I was talking about how recently advantages have been made not only through new materials, but through modulating the packing of materials. And amongst the Y family of acceptors, we can certainly identify many cases where, with small changes in chemical structure, that brings about significant changes in packing, in the crystal structure, and significant changes in the behavior of the material. And so this is really just to sort of, to demonstrate that it is now possible to take our chemical structure and our crystal structure, and then to do some analysis. We can first of all try to validate that the model is okay by reproducing absorption or emission spectra, and then we could speculate on what the charge generation efficiency might look like. And this is here demonstrating that if you just apply your field along different crystal axes, you will have a different performance, or if we increase the amount of disorder, you would have different performance, and so on. So there's a capability there that may be useful to exploit in the future. So I've got now an emergency button to jump to the end. I don't know if I can actually press it. No, I can't. I just jump, it's easy, I jump through the rest. My last few slides were really just about how you can use the same framework to look at other types of energy conversion, and could be done in organic photocatalysts, something which a lot of people are looking at nowadays, and they've got a lot further to go in terms of reaching limits to efficiency. One thing that we're interested in is in applying the same framework to photosynthesis. And in that case, I'm much more optimistic about the efficiency. And I will tell you that there are still interesting problems to look at, and amongst them, is this problem of how it is that certain photosystems are able to do photosynthesis using longer wavelengths of light than was previously thought possible. And that's done by introducing this is an image of photosystem 2, introducing into photosystem 2 a few pigments which have about 100 millielectron volts lower photon energy than the rest. But importantly, one of them is in the position of the primary donor. And what that means is that we're driving the same photochemistry. We're splitting water, but with 100 millivolts less energy than was previously thought possible. And that's something which is very interesting. And in order to try to understand it, we're using all the same apparatus, but applied to a different structure of materials. And the answer, I can tell you, lies in exactly where you put those far red pigments inside your photosystem. So I'm going to finish. Ellen will be happy with just a few remarks. So in terms of trying to model the behavior of our organic solar energy conversion devices, the apparatus that's provided to us in terms of transitions between excited states, between different molecular states, is actually quite good, and it allows us to relate the chemical structure, the molecular structure, and indeed the packing of the materials to the performance of the device. It's just important to make sure that you couple your charge transfer state to the pulls of mobile charges. When we look at what the limits are, we've seen from the open circuit voltage that the thing which is the strong thing which is limiting photovoltage is the strong electron-phonon coupling between the excited states and the vibrational modes of the materials. You can modulate that up to an extent, but to modulate it a lot, some radical changes in design would be needed. We see that the driving force for charge separation from the charge transfer state depends on many things, but when you get to the limit of a low offset, actually what you want is a long-lived excited state in order to avoid the initial photoexcited state as acting as your loss pathway. So we think that favorable molecular properties could be designed in, but we probably will need to find a way of dealing not just with single molecules that you could solve quite nicely in quantum chemistry software, but a way of dealing with extended states. And so with that, I finish. I'm going to thank my group members who have been critically important in all of this work, and you for your attention.
Thank you, Jenny. There's very little time for questions. Maybe do one? Ole.
How do you put a single dye molecule in a green plant exactly where you want it? How do you know that you put it there and that's there where you want to put it?
This is a question that I've had, and I say this to my biochemist colleagues, and they say, "Oh, you just edit the genes."
Oh. So
they say, "Come over to the lab and we'll show you."
Okay.
It's not that easy, but it can be done. In this case, this isn't something that we made. This is something that existed, it was discovered, it was grown, and now in collaboration, of course, we're trying to modulate it, and there's been some success in editing. Of course, there's some control in terms of whether you have a red or not. At a later stage, of course, we would like to be able to put them here, but they're. I don't understand it at all, but this is what I was told. You just edit the genes.
But then the comment, if the 100 millivolts that you said that you introduced was already done in some of the systems.
It exists.
So nature has been there.
It's been there. It's been there, discovered about 15 years ago. Mm-hmm. And then the mechanisms are kind of quite an intense area of investigation at the moment. Yeah. So the important thing is that it's this lower energy pigment which is doing the photochemistry, which is the last spot before charge separation. So
we have to close the discussion, but there will be a coffee break after the next talk, so maybe you can catch Jenny then, right?
Okay.
Thank you, Jenny. So then I invite the next speaker, who's Anna Köhler. And Anna from University of Bayreuth in Germany is going to talk to us about this disentangling exciton dissociation pathways in the non-fullerene acceptor 0.6.
Thanks a lot. Thanks a lot for inviting me and for having me here, and for you as an audience to still be patient. It's the middle of the afternoon. I thank all the previous speakers for already introducing the topic of organic semiconductors, why they are important, why we look at solar cells, and in particular, why we look at Y6. We have been looking at solar cells for quite a while, I think already for the last 30 years, and we understand them better and better. And one of this morning's speakers has already shown that we started off with homopolymers, added the acceptor pretty quickly, had homopolymer with fullerene. Then we had copolymer with fullerene. Then we had copolymer with non-fullerene acceptors, which were of the acceptor-donor acceptor type. And all of this helped to improve the efficiency. So the status we're at the moment is copolymer with acceptor-donor acceptor type molecule. And one of the things we learned when we actually studied these compounds is that morphology is important. I mean, first of all, what you actually have is you need to have a blend of a p-type and n-type, you could say, material between two electrodes. Your light comes in and it generates an exciton that diffuses to the interface. And we've all learned at the interface that's where it actually separates. So, okay. So that's what you actually have. And over the last 10 years, we looked into this process in itself and the efficiency of it. And among the things we actually learned is that separation process is rather poor. You get more recombination than separation if you have got disordered polymer chains and if you have got amorphous molecules. On the other hand, if your polymer chains planarize so that you have got delocalization of the hole along the polymer backbone, or even interaction between different chains, it works much better. Similarly, if you have an electron that can actually delocalize over several adjacent molecules, such as a more crystalline acceptor compared to a non-crystalline one, you get a more efficient separation. This is all stuff that we think we understand by now. We understand the reasons behind it. But the thing I want to look into more now is what happens if we have a single material in itself, and how does this separation process actually happen? And what's the role of morphology in all of this? The tool I'm using is actually spectroscopy. Spectroscopy is really nice. And by that I mean optical spectroscopy, because whether or not you have got disordered or ordered material will have different signatures. And that allows me to look at a short range order. I don't necessarily need a GVAX and long range order in order to detect something. And it is an order on the short scale that matters for the separation. By short, I mean compared to intermolecular distances. So 10 nanometers is already a lot if your chains are only 1 nanometer apart from each other. The reason why we look at PM6 and Y6 is, of course, because they form part of those material systems that have basically pushed organic semiconductors to the 20% range. And I mentioned already, it's a morphology that is important for it. PM6 itself is a semi-crystalline polymer. You can basically show if you heat it, the absorption and emission changes. It becomes very broad and unstructured. You cool it, you see the structure, so you know it's semi-crystalline. Y6 is similarly intricate. When we started looking at PM6 and Y6, it was actually in a collaboration with Derya. And he pointed out to us that his student Lorena, she had looked at a compound, at a solar cell, and she took the PM6 and added Y6 and made solar cells, and reproducibly in these non-optimized cells had 14% efficiency. It's fine. She used N4 instead of Y6, and she only got 12%. Now the difference between Y6 and N4 for the physicist is nothing. For the chemists, it's still something, but nevertheless it's small. The only difference is here in the branching point of the side chain. Y6 branches closer to the backbone and N4 branches further away. What that does is it affects, of course, the molecular packing. But the effect it has is significant on the efficiency, and with all the electrical characterization techniques Lorena had in Didanea's group, they basically show that there is a lot more charge trapping going on when you have the N4. And we wanted to understand why. Why does inserting 2 carbon atoms, 2 carbons is nothing, have such a big effect? And in order to understand that, my student Toby took a solution of Y6, and he wanted to look at how its spectral signatures depend on the quality of the solvent. And there are 2 ways how you can change it. You either take a good and a poor solvent and you mix it, or a simpler way is you just take a solvent, a good solvent, and you cool it down, because that also essentially reduces the solvent quality. If you do that, what you see is, first of all, if you look at the absorption versus energy, the absorption increases. Now, how can that be? After all, the molecule cannot become any longer. It happens because as you cool down, or what it tells you, is that the molecule must have become effectively more planar. You have less rotation. Otherwise, you couldn't have a larger dipole moment in there. You have a larger effective conjugation length. You cool down even more, and the next thing you see is that a new feature is coming up, while the previous one is actually going down. So evidently, there is a new species forming, some kind of aggregation. You cool down even further, and the same happens again. If you go below 195 Kelvin, you see a new feature coming up at the expense of what was there previously. Okay, we cool down. You have seen if we make a solvent bed, we get different polymorphs essentially of this compound. What about N4? You do the same to N4, and you see similar features, yet with different details. First of all, the point where a new feature arises is at a much higher temperature. It's 320. 320 is a comfortable room temperature. For Heinz, it would even be too warm. For me, it's comfortable. Anyway, that is because the branching point is further away, and as a result of it, it is much easier for the pi system to pack than if you are having bulky side chains near the backbone. You can understand that. And the other thing that you may actually notice is that whereas for the Y6, a new feature was coming up at lower energy, for the N4, it is coming up predominantly at higher energy. So it looks like the one has more of a Y kind characteristics, the other one overall has a bit more of a H type characteristics. So far, so good. What does this help us in understanding our solar cell? It helps understanding the solar cell because, let me go back 1 point more, once you have done this in solution, you can of course identify your spectral signatures. You know that the feature at this energy here is from a non-interacting Y6 molecule, whereas the one below is from Y6 in an aggregate, or for N4 correspondingly. And once you have done this in solution, you can go and look at the neat film. If you have the neat film, you still have one compound, but the spectra tend to be a bit broader. Having done it in solution first helps you to identify your features much easier. And once you understand what you see in the neat film, you go further to the blend. And then you can compare your absorption in the blend, for example here, PM6 with Y6 and PM6 with N4. The differences in absorption are subtle. But if you actually analyze it, you see, well, you've got part that's just from the PM6 at higher energy, and then you have got the Y6 part at lower energy, and you can clearly say you have a contribution from non-interacting molecules, but also some contribution of the one polymorph and the other polymorph. And the difference between the two compounds is just how much you have of each of them. In the Y6, you have most of the low energy compound. And that is the key in that case to it, because what happens if you photoexcite your sample? Well, the hole will be on the PM6, the electron will be on the Y6, and within the Y6, it will of course go to the lowest energy Y6 phase available, which is this really lowest aggregate. If you have enough to make a percolation path, you get it out easily. If you don't have enough, it might actually be stuck and trapped somewhere on it. And that is what ultimately there are a few tricks in between forms that trap states that we have and reduces the efficiency. That's great, we understand what's happening in the steady state. But we would like to understand quite a bit more of what the actual charge separation process is in, for example, just Y6. So let's go for that. Let's take just Y6 and understand it. And as Jenny and also Gwyn have already introduced, there has been lots of work on it already. There are suggestions that we get a lot of polarons, almost 70%, and that they live only a very short time. But in these studies, people mostly focused on single crystals or polycrystalline material. They only considered single crystals in their explanation. Yeah? They did not take into account that you may also have some non-interacting molecules that are there. There are also other experimental reports that show that you can actually have polarons which live for 10 nanoseconds. And then there are reports that suggest perhaps the disordered phase, so a phase of non-interacting molecules, needs to be taken into account and energy transfer between the two. Keep in mind that I'm talking about small length scales. I'm not talking about 200 nanometers. Yeah? But something may be there. So we looked at that and I wondered how to make sense of all of this. And in order to understand it better, we did what we've done before. Let's just look at it first in solution. We took the Y6, and if we want to do pump probe spectroscopy, which is on the short time scale, you do not want to do that in a cryostat at low temperature, because cryostats have multiple windows, you get lots of scattering, and that messes up what is already a complicated signal. Let's stay at room temperature, and let's therefore take a good solvent such as THF, it's polar, and a non-polar solvent such as cyclohexane, it's a poor one. If you have only THF, you can see here as a function of energy we have absorption and we have emission. We now add a bit more of the bad cyclohexane to it, and what you see is you still see nothing. Now you see it, yeah? You still see only absorption at the same energy, so we still have disordered molecules in there, non-interacting ones, I should say, because we're in solution. Yeah? But they have become, the absorption has become more narrow. And the emission has shifted to the blue. It's a small change, but what does it tell us? I mean, if it has become more narrow, obviously we have less disorder. We're still at the same energy, but we seem to have less rotations in particular. And the blue shift is easy to understand as a solvadochromic effect. You are now in a less polar solvent, so obviously your excited state is not stabilized as much anymore as it was before. It's important to keep in mind when you compare your data to whatever is in the literature, always consider what's the environment in which your Y6 was. Which solvent was it? Was it in a film or a solution or whatever? We now increase the actual amount of poor solvent, and that's when we start seeing the new feature coming up, absorption from the aggregate. And in emission, an aggregate emission adds to it, but in addition to the emission from the disordered chains. Again, shifted a bit blue because we're in the nonpolar solvent. And if we excite at about 1.5 eV, so that would be here, 850 nanometers, below the onset of the disordered absorption, you then see only the absorption from your aggregates. That's nice because it helps us to first of all see what do we have. Yeah? And if you go for the higher one, you have even more of it. So we can clearly say that's in absorption, our disordered chain, disordered molecules, that are the interacting ones, and the same for emission. It helps understanding this before you actually try to look at your pump probe spectra. If we look at the pump probe spectra, we have here for different times in different colors the spectra. One thing we do is we excite our material, thereby promoting an electron, then we come and probe. As a molecule is already in the excited state, it won't absorb any more, so you have a ground state bleach signal. Clearly that should look just like the opposite of absorption. So we have shown the absorption as a negative signal here in gray. So that part is what must be the ground state bleach. Another thing that can happen is that your probe beam actually triggers an emission, so you have a stimulated emission. And the stimulated emission is basically exactly like your PL spectrum. So the red part is your PL spectrum from the steady state. Therefore, what you see here from 100 picosecond onwards is a stimulated emission. But at shorter time scales, it was bluer and it merged with the ground state bleach into one feature. I will come back to that. Maybe I mention it now. What's actually happening is that right after excitation, it's further blue, further red, blue, and then it shifts as a result of solvent reorganization within 10 picoseconds. And then in addition, you have your absorption from the excited states. So we have all these features very clearly assigned for non-interacting molecules. Now we can look at the aggregates, and we excite only aggregates if we excite at 850. We again see excited state absorption, and what's particularly nice is we have some ESA feature that is not overlapping with what you actually have in the disordered ones. So that's a clear tell sign. And then we have got the ground state bleach from the second excited state. But of course, we cannot see anything where we would expect the ground state bleach and stimulated emission from the aggregate, because if we excite at 850, we can't detect at 850 unless you kill your detector. You've got the scattering from your laser point. So therefore, let's actually excite both. Let's excite at 410, where you excite both, and you compare with your absorption and your emission, and it becomes rather clear. Good. This is your ground state bleach and your stimulated emission from your aggregates. And you also have a bit of excited state absorption still from your non-interacting chains. These were just the spectral feature. Now let us look at the time, since we want to see how things evolve. For the non-interacting compounds, you can see you have your ground state bleach signal, and that lives for about 1 nanosecond. Same for the excited state absorption, because it's from the same state. And you also see nicely this redshift of our stimulated emission. Fine, we understand that. So photochromic effect within the first 10 picoseconds. Now we look at only the aggregate. So we took the 1 to 9 solution, excited at 850, only aggregate is excited, nothing else. And it only lives for about a comparatively short time. Here we have got 30 picoseconds. And we wondered, what is this? Why does it live for only 30 picoseconds? It's consistent with the earlier reports from other people, but which non-radiative process would be so fast, such as to quench it, if you have just aggregates in solution? Anything that I can think of is longer, reasonably. We also looked at this 410 excitation, where we excite both, and it's just essentially a superposition of the two separate spectra. So back to the question, why does our ground state bleach in our aggregates decay so fast? What is happening there? To explore that, we use different excitation fluences. So we looked at low fluence, medium fluence, high fluence. The spectra at longer times all look the same. But if you look at the evolution of some of the signals, for example, in particular at the ground state bleach and the excited state absorption from your aggregates, you see for low fluence, they live for about 300 picoseconds. And the more you actually crank up your laser, the higher your power, the shorter they live. In contrast, your ground state bleach that you actually have from your non-interacting compounds, that's the feature here at 1.7 eV, yeah? That is always at 1 nanosecond and completely unimpressed by the laser power. Now that smells strongly like a singlet annihilation process. It's a bit unusual because the powers we use are not that high, yeah? But it looks very much like it. So one other feature is there, if you look closely, you can see beyond 1 nanosecond here, there is actually a feature that is living for longer. So our singlet on the non-interacting chains has decayed, but there is some feature that continues. In fact, you have the excited state absorption and the bleach, they are both there. It's not this, it's shifted a bit to lower energies if you look carefully. It's for all of them. If we look into this singlet annihilation process a bit more carefully, what we can do is we take the ESA feature that we had and plot it as a function of time for the different fluences, and you can nicely put mono-exponential decays through it. Okay, once we have that, we get the lifetime. The lifetime is just the opposite of the rate, so that's the rate constant for the decay of our excited state on the aggregate. And it increases linearly with pump fluence, whereas the ground state bleach for the non-interacting ones remains completely independent of pump fluence. So it's a very clear sign we have singlet annihilation. And it allows us to extract the spectrum for the polarons. If you look at 1 nanoseconds after excitation, you still see the ground state bleach and SE from your non-interacting molecules, but after 1 nanosecond, that is gone. And anything that is left lives for really long and is a signature, the ESA and the bleach from your polarons. And evidently they seem to sit on the low energy side of the aggregates. So we can actually put things together if we excite only our non-interacting compounds, and we can excite S1 and or Sn, it doesn't really matter, you always end up on S1. We have our different features, excited state absorption, ground state bleach, and perhaps one detail I want to point out is, the ground state bleach is always at about 1.8 eV. The solid line is if you have got just the polar solution. The dotted line is if you have got the less polar solution, and that's when your stimulated emission shifts further to the red because of the solvent because of the lack of solvent relaxation. Yeah, so that feature varies depending on how polar your environment. That's a detail to be concerned about when you assign your features. You just have to know it and keep it in your mind. Right. Then for the aggregates, if we excite it, we get singlet annihilation, and as a result of it, very fast decay depending on our pump intensity, and we can actually get the feature, the spectrum for this, simply by comparing our sample where we excited both, or where we excited only the disordered ones, and then subtract it from the difference. And we can also look at long times, such as a few nanoseconds, yeah, in the And there, from that, we get our spectral signature from the polaron. And we can even tell how much polarons we create from it by simply comparing how much ground state bleach we had initially and how much we have later. Yeah? So this part turns out to be about 5 to 10%, and it happens very fast because the signal is there right from the beginning. If we now go to the film, the spectra look similar. I don't show them for you for lack of time, but they are in the paper. You can have the additional energy transfer, in short, between the disordered and the ordered shades. There are small differences. For example, your thin film spectrum that is shown here in light blue is further red for the non-interacting ones, but further blue for the interacting ones. And first I was quite confused by that until I realized in the non-interacting ones, in the film, it's further red because now you can have spectral diffusion. You get to the lower energy sites, which you don't get in solution that easily. On the other hand, if you then look at the aggregates, why should they be shifted? And we actually realized they are shifted because if I'm in solution and I have got a mixture of good and poor solvents, the aggregate forms by planarizing and then sticking together, and then more and more of them add on. It's a nucleation and growth process. And if you do that in solution and you're a careful and slow student, you're close to equilibrium, it's a gentle process. The same happens if you do your film, if you spin coat your film. As you spin coat and the solvent evaporate, but it's not nice and gentle anymore. You still form your aggregates by nucleation and growth, but the process is much faster. So you will actually end up with shorter aggregates. And that is what I think is happening and how I can account for the fact that we actually have got all the spectra shifted a bit further to the blue. So this is just illustrating how we can get the 5% value for the polaron yield. Let's look at the polaron generation mechanism. I suggested that it should be an Onsager mechanism. If that is true, then our photocurrent should actually rise quadratically with the offset from the electrical gap. So we put the Y6 between two electrodes and we measure the quantum yield of the photocurrent. You have a little bit of extrinsic one, and then as you come beyond the optical gap, it rises. What we have done here is you can see the difference from the electrical gap plotted as a root versus energy, and it rises very nicely linearly until other things happen. And we determined that electrical gap by electrochemical impedance spectroscopy earlier on. So in which way is Y6 special? We have seen we can get this photocurrent by singlet-singlet annihilation. It can happen in many other compounds. What is special about Y6 is that it is very prone to aggregate formation and it forms extended networks. So you see the effect more strongly. But you can have polaron generation by exciton annihilation processes more commonly. The easier way of doing it is, of course, by using triplets. For example, by making a single layer solar cell, once with P3HT, where photoexcitation creates very few triplets, and once with actually a TLDF host material that Chihaya Adachi also mentioned this morning, where you have more triplets. If you take the P3HT, you can measure absorption and emission and determine your singlet energy, and you can measure your photocurrent, that's in green. It only raises well above the singlet state. You can also measure the amount of charges that have been photogenerated by a technique called thermally stimulated luminescence measurements. What you do there is you cool the sample, irradiate it, that creates excitons. Exciton generates germinate pairs get trapped. You stop irradiation, you wait, you heat, and they get, say, detrap and luminesce. And you can see that the yield for that process is much, this thing is going to drive me mad, is much higher as you come to higher energies. Right. If you do the same with actually the TADF emitter or TADF host material, MCBP cyan, you can again measure absorption, emission, determine your energies. You see both photocurrent and thermally stimulated luminescence set in rather sharply, exactly at the singlet energy. You excite the singlet state and you get free charges. Why do we get free charges in a single layer of a TADF compound? Is it the new Y6? Well, it's not quite as efficient, but it happens. Again, you do your standard characterization work. You measure photoluminescence and delayed fluorescence as a function of intensity dependence. You measure the photocurrent as a function of power, and you realize you're having triplet annihilation, and that is what is causing your charges. You can even look at it as a function of temperature, and you nicely see in green how your phosphorescence goes down as you heat. Your delayed fluorescence goes up until you have so much triplet diffusion that it diffuses to trapping sites, and you see the same evolution for the photocurrent, but you have an offset because of the exciton binding energy. You need that additional energy to get further. So you have the same process, and you can analyze it quantitatively in terms of Onsaga theory. So it fits really nicely. So if I put together where I am, it's what I want you to take away is actually, if you look at your thin films of your compounds, keep in mind that you may have multiple phases. If you neglect that you are also non-interacting chromophores, you may make misleading assignments. Stuff that is actually just from non-interacting chromophores may accidentally be attributed to polarons, for example. Yeah? If you want to identify your spectral features, start simply. I mean, that's my message in particular to the students. Start with the simplest system you can think of, just one compound in solution, then one compound in film, then two compounds. Don't start with two compounds in the film right away. And for the Y6, we think the mechanism by which we generate these charges in the neat Y6 is a simple autoionization in the Onsaga spirit, reached either by singlet annihilation or even if you excite it directly. And finally, that's where Y6 is special, because you have a good aggregation in there, and it can also happen for other compounds, but with triplets. And with this, I would like to thank everybody who contributed to it, in particular Dani Groh, and I had lots of help and suggestions from Heinz Bessler, I should mention. We had funding, good collaborators, and in case this session so far, this morning, made you interested in organic semiconductors and you want to learn more about it, you have a second edition of the textbooks that Heinz and I wrote that came out.
Thank you so much, Anna. And there's 5 minutes for questions.
Oh, Richard. Richard, yes.
Anna, lovely talk, as usual. The business of singlet collisions to form polarons, on the face of it, is a bit of a worry, because but I presume that happens at fluences much higher than under CW solar radiation.
There were 6 microjoules was the lowest we had, and then the other ones were higher, and 6 microjoules per centimeter square is already quite a bit.
It's several suns, isn't it?
Yeah.
But I imagine that the reason that the threshold for that is quite low is because the diffusion coefficient for singlet excitons is quite high.
I think 2 things come together. One is the diffusion coefficient is high, but also the extent of the exciton in this aggregate is quite large. I put on that one paper from our colleague Stefan Kümmel, where they looked at the extent of the CT exit or of the CT exciton in neat Y6, which can be quite large. And I think that the aggregates we have in solution and in film are not that small. Otherwise, you wouldn't get that cross section. You think about the numbers and the timescales, And first I was worried and thought, can that be? Is this an error? But I think that's the reason why.
Well, thank you very much for a nice talk. If annihilation is dominating decay, and I thought that the single annihilation, wouldn't you expect it to be non-exponential? I mean, it's a second order process.
The ESA
The decay, I mean, would be
decaying.
very non-exponential.
We fitted it with an exponential, at least on that time scale, and it looked good.
You see what I'm saying? I mean, it's a second order process, kind of.
If you have got a distribution of distances, then it should be non-exponential. Maybe that distribution isn't sufficient enough to show up significantly. Yeah. I should mention, when we looked at the slope, you have a mixture of singlet annihilation and direct excitation, because we excited also at 400.
Okay, more questions? I don't see any more hands. Then let's thank Anna again.
So it's my pleasure to introduce after each other the two Nestors of the field, I would say. First, we start with Carl Leo from Dresden University in Germany, and then later we'll move on to Christoph Brabeck, from also from Germany, but from FAU and the Forschungszentrum Jülich. And let's start. So Carl, please welcome to the stage, and Carl is going to talk about the topic that is on the screen here. Please go.
Well, first of all, thank you for the invitation to this wonderful meeting here. Ellen, Feng, and Ole, this is extremely nicely done, perfect organization in such a beautiful city. I prefer it highly to traveling these long flights to Honolulu, and it's much nicer to be here. Also, you must be tired, so my sunset Dresden with the organic moon going up fits maybe nicely to the time of the day, but I hope there is some things which will entertain you enough to keep you awake. So I think if one looks at sustainability of current electronics, it is pretty much clear that we cannot continue the current way we do electronics is unsustainable. First of all, due to materials usage. You see here all the materials which are used in current nowadays electronics. And for instance, tantalum alone is a reason to do things differently. Obviously, another problem is energy usage. I don't want to discuss this now, but artificial intelligence, for instance, is using enormous amounts of energy. At the end of my talk, I'll spend 30 seconds how we might do that better. And maybe the worst disaster is how we dispose electronics. We produce about 7 kilograms per person per year worldwide. And out of that, 22% are recycled and 78% are unaccounted, meaning usually ending up in dumps in Africa where people waste their health to burn some copper and other valuables out of it. So obviously, we need new approaches, new materials. And I'm talking about organic electronics, and therefore I advertise the fact, just take carbon, it's everywhere, it's non-toxic. And you can dispose it because you can put it everywhere, at least with some limits. And the most discussed topic today is organic photovoltaics, which obviously has a lot of advantages. First of all, it's basically an inexhaustible materials class. It's non-toxic, and that's maybe also unique among many of the emerging materials classes. Secondly, it's flexible and lightweight, which is obviously nice for solar cells. It can be very efficiently manufactured by roll-to-roll. It can be made transparent, which is also interesting for many applications. And it has a quite nicely looking homogeneous surface. And many people have in the last decades worked on it. My group has done a long time of a large amount of work on organic solar cells. And in a kind of relaxed way, I'm summarizing this in the next slide. You know, we started more than 20 years ago with this, our little small glass samples, and after spending many years and a lot of money, mostly with our spin-off company, we are now here at commercial organic PV modules. So they are on the market, they are certified, and the technology is working. And me personally, once something is commercial, I'm trying to move to other fields. Because I leave the commercialization to people in spin-offs and companies. Mass producing things is very hard. I know that since being at Fraunhofer Society, and I usually prefer to do basic research where a yield of 1% is good enough in research sometimes. But I will give you a little overview about where the organic commercial organic PV stands. And the real most important breakthrough, obviously, in my opinion, was when we got this certificate here. And this is the IEC 61215 certificate. And you can't sell commercially any photovoltaics without it. And Heliatech was the first company, and I think they're still the only company which was able to pass these certification tests, which basically guarantees a lifetime long of 20 years, which we actually tested over many years, not 20 years, but many years in Singapore, the worst environment you can imagine, humid and hot. And therefore, these cells are now really ready to work long time outdoors. The stability is not really limited by the organic stack. Maybe there's a little weak point in the C60, which is still in these cells, but otherwise it's mainly the module which makes the difference. Now, actually, if you move out of solar cells, there's actually a very easy way to come to a new field, but you don't need to read too much new literature, and that is going to photodetectors, which I'll do in a moment. But first, I want to come back to the sustainability issue, and this is really, I think, maybe the most important message of the organic solar cell field, and that is the carbon dioxide budget. And Heliatech has done a study. If you manufacture 1 square meter of these flexible modules attached here, you produce 16 kilograms of carbon dioxide. What does it mean? More important is this number here. You produce 7 to 9 grams of carbon dioxide per kilowatt hour generated. This is in Central Europe, in Italy or in the desert somewhere it might be better, but this is a very good number. The one point you can kind of explain this number is by the energy feedback time, and this is 3 months for these modules in Germany. In other words, it's about 4 to 10 times better than crystalline silicon. And this number of 7 to 9 grams per carbon dioxide is comparable to water power, which is the other technology with the lowest carbon dioxide generation. So it's a wonderful technology. It is really sustainable, non-toxic. But despite these many applications which you've seen and the maybe more than 100 big installations Heliatech has made so far, it is not the big commercial success. As you know, people still mostly buy cheap silicon modules, despite all the environmental problems they might have. And the answer is quite simple why they do that. First of all, organic PV is more expensive than silicon. And that is not because of the organic materials, but it's mostly because of the module, the encapsulation foils. If you want the plastic foil, which survives 20 years on the roof, it's expensive, more expensive than maybe a sheet of glass. And the second point is the efficiency. And obviously in photovoltaics, if you have 10% instead of 20%, you have twice the cost because you need twice the area and the materials are area proportional. So obviously, we need to work on this, and the key point is to increase efficiency. We know from many talks today that we are now with organic PV above 20%, but when it comes to manufacturable, stable, and so on, we are now at about 10%, and to close this gap is a major point. As said, we moved in the last few years more to photodetectors, but one point I want to make is today, if you make a very good photodetector, you learn also a lot for making better solar cells. So we kind of feed back the information we gain from photodetectors to solar cells. The main difference for a photodetector is that there's more than efficiency and price. The key property is the specific detectivity, basically signal to noise, but factors like speed, dynamic range, spectral properties, broadband or narrowband, and some other points are also very important. And in many cases, you need to optimize one of those parameters, and then you have to do different things than in the solar cell. But still, I hope to show you in this talk today that if you make better organic photodetectors, OPD, you make also better OPV. And therefore, this is also useful for the solar cell field. Now, I said the main parameter is detectivity. That's basically signal to noise. And the detectivity is shown in this diagram here. You see the classical silicon, indium gallium arsenide, germanium photodetectors. You see a lot of organic detectors, and you see that many of them are in a similar ballpark than the traditional semiconductors. You also see the thermodynamic limit up here, and it is obvious that we are still, with all those systems, far below the thermodynamic limit. Now, if you look at the equation for the detectivity, it's basically signal to noise, and signal is external quantum efficiency, and noise is noise spectral density. And the spectral noise density is usually proportional to the dark saturation current. There are many noise sources, I don't want to discuss it in detail, but typically it boils down to reducing the dark saturation current. And it's really a very basic knowledge that the dark saturation current is very closely linked to the VOC of a photodetector or a solar cell, and basically by reducing the dark saturation current, you can improve the voltage losses. That's clear. So both the EQE and the noise are very much related to properties which are also important in solar cells. And in my talk, I will address three different topics. The one is discuss these reverse currents in more detail, especially their relation to heterojunction. Then try it without a heterojunction, and finally with a completely different device, a phototransistor. We know the main problem of organic photovoltaics, that is the exciton. The gallium arsenide exciton is a big weakly bound chunk, and the organic exciton is basically on one molecule and has a binding energy much, much larger than KT. So usually you don't generate carriers directly. Qing has made this seminal discovery that with a heterojunction you can separate it. And later on, several groups, the first one, Masahiro Hiramoto, showed that by blending the donor and acceptor, you can overcome the diffusion length problem and collect many of the excitons. Now, obviously, when you generate such a bulk heterojunction, you generate a complicated morphology, which must be on the nanometer scale, which might cause stability problems. And actually, it creates many other problems. And I start with a little study we published some time ago, studying the reverse dark currents in organic photodetectors, measuring the noise, and looking on how we can improve it. And this was work done by Jonas Koblitzky, who is shown here, and he looked at a number of simple donor acceptor systems here with these different donors, and very carefully studied the photodetector properties, including the dark current and the noise. The first step he did was a very simple experiment. He varied the thickness of the devices, and therefore came to the conclusion that in these devices the shunt currents are not dominating. In any real diode you have some shunt currents, but he could nicely show that here in these devices, actually the thinnest devices had the lowest reverse current. So that is a very clear sign that shunts, usually by metallic filaments, are not really important. And then he looked at the blend ratio in the bulk heterojunction from, in this case, 22% down to a diluted system with 6%. And there's a very, very nice and clear trend of the reverse dark current with the blend ratio. The less blend ratio you have, the less you have in the system, the less you also have dark current. And this scales not only with the reverse current, but also with the noise. And therefore, obviously, the interface in the bulk heterojunction blend itself seems to be a problem. We've heard a very nice talk from Jenny and also from Anna, and they showed that this is a well-known phenomenon, and that obviously the complications at the interface can cause such effects. And then Jonas studied the trap states in these devices with a very careful impedance measurement, and he was able to actually determine the trap concentrations and the trap energies as a function of, again, the blend composition. And again, it beautifully scales from the highest ratio to the most diluted system. The trap concentration scales perfectly. Look at the numbers. We are, for the highest concentrations, in the few times 10 to the 16th, which means that, very roughly spoken, about every 1,000th molecule at the bulk heterojunction interface is associated with a trap. Obviously, it's nice to see that we do have traps, but to really improve, we need to find out the nature of the trap. And we studied various systems. We also studied sensitive EQE, but I must say that as of today, we don't have a really microscopic explanation. The parameters of these traps are quite nicely known. They are pretty much at half the CT energy. They are about at half an electron volt. The CT energy in this system is about 1 electron volt. So unfortunately, in terms of the Shockley-Hall theory, they are at the worst energy, and they are most efficient for reverse current generation. And we do have some speculation about possible reasons. We pretty much believe that there are not chemical impurities, because we very carefully studied the purity in these small molecule evaporated materials. You can do that by simply varying the number of sublimation steps. So if you do only one sublimation step, you have a more impure material. If you do several, it gets more pure, but these traps didn't worry about that. They were always there. So they seem to be some more intrinsic structural point. And we did other studies. I don't want to discuss here in detail, but we showed that for various zinc PC and zinc PC derivatives, that the orientational property of a surface has a massive influence on the ionization energy. And you can easily, if you look at it in photo emission, for these two different systems, zinc PC, F8 zinc PC, you see that the ionization energies vary by about half an electron volt if you go from this to this orientation. And one speculation is that obviously at the bulk heterojunction you have a disordered system, and once in a while you might have a position like this, and once in a while like this, and then you might have your half electron volt trap you need. We very well know, and this is also discussed, I found a recent paper from Alan, that in polymer systems this is absolutely the same. There are changes in the orientation of the molecule dependent on the film thickness, and therefore in a bulk hetero system, by the orientation themselves, you might have a major source of traps already. So the point is, we know that now, but as said, we haven't really solved the problem. Now, what can we do to avoid it? One very simple approach is to minimize the interface area if we know that we have traps at the interface. And that we did in this study. This was very nice work done by Tianyi Zheng and Johannes Bendun. And the original idea of the study was actually more to look at rubrine devices. Rubrine devices because we expected them to be very fast. In previous experiments, we had measured very high vertical mobilities in rubin of about up to 10. And we had used that for a very nice and new device for realizing an organic bipolar transistor, which actually came almost 40 years after the first organic field effect transistor was realized, just the opposite like it was in silicon. And there we knew that rubin can have high mobility, high diffusion lengths for the transistor, and therefore we wanted to make a fast photo detector. However, in the course of this work, using rubin C60 as the active system, we also compared bulk and planar heterojunctions. We did a number of other measures to optimize the reverse current. We used molybdenum oxide doped underlayers, and we also played around with the whole transport material. The main conclusion we finally made is that in the planar heterojunction, actually, we had by far the lowest dark current, which you can expect because the area of these defects is the lowest. And therefore, we actually got very good photodetectors, not only in the speed. We reached about 400 kilohertz, which was a little bit disappointing. We expected higher speeds. But we obtained extremely well linear devices with more than 200 dB. But the most important point was due to this very low reverse dark current, we could actually realize extraordinarily high detectivity. And you see here, this is the data point, so it's probably the best blue photodetector made. And you see it's more than an order, or almost 2 orders of magnitude better than a silicon photodiode. You know, that makes me really proud. Coming from real semiconductors in my early career, I'm now in this dirty organic stuff, and it works better than silicon. That's nice. So we learned, take a planar heterojunction, and you can make a very nice photodetector because you avoid the dark current. Obviously, the EQE is a little lower. That's the price you pay, and that might not be the good solution in the solar cell. So the next idea is then, well, if the planar heterojunction is not so good, why don't we get rid of this heterojunction at all? And that we did in a recent study. This single component OPV and OPD is not a new field, and there has been a lot of work on single material stacks, especially in polymer devices. And in polymer devices, people have reached quite high efficiency, 14%. And there's a large amount of literature. But there's almost no literature on small molecule OPD, especially vacuum prepared small molecule OPD. And therefore, we looked at it. If you look at the polymer work, actually, the single component device is kind of a little trick. The trick is simply that you synthesize a polymer which contains donor and acceptor, and then you have your heterojunction in one material. That is a nice idea and works beautifully, but for evaporated systems it doesn't work because the donor acceptor systems would be too large to evaporate. So we couldn't go this way, and therefore we tried it actually with real small molecule single component materials. This was work by Jakub Wolański and in a very nice collaboration with Natalie Banerjee and Frank Ottmann. And the molecules actually were well known to us. These were thiophene derivatives, which were synthesized from Peter Beuerle for our earlier solar cell work. He did hundreds of these molecules for us and for Heliotech, and they produced quite nice solar cells in evaporated systems. And we simply compared the standard bulk heterojunction device with a single component device where we carefully aligned everything that you don't have an unwanted interface. And then Jakob showed nicely that in the bulk heterojunction in these devices, you get about 60–65% historical quantum efficiency. But in the single component, single layer, without any further measure, you are almost at 20%. And that was quite surprising to us. We had never checked that before. Furthermore, as we've nicely seen in Jenny's talk, when you apply a little bit of an electric field, you can actually raise this quantum efficiency quite a bit. And here in the single component layer with about -3 volts, you are almost back at the bulk heterojunction. So with a fairly small field, you can get a very good charge separation, and you can produce a fairly good photodetector without heterojunction. Now, obviously, the question is what's going on here? How is this possible? And there, the group of Natalie Banerjee came in because she is very good in transient absorption, and we studied the devices. We studied actually neat films and also the device stack. What's the difference? The neat film is the film itself. The device stack contains the transport layers, the dope transport layers, and therefore it contains the built-in field. And you shouldn't underestimate that the built-in field helps already quite a bit. I don't want to discuss the analysis, but you can nicely charge, separate charges, excitons, and triplets. And here, this is the main message. You see here the excitons and the charges in the single component devices. And you see that in the neat film, the charges need some time. They need about 100 picoseconds to show up. The excitons immediately decay. And if you go into the device stack where you have the built-in field, actually the charges are there right away. After 100 picoseconds, you have already a lot of charges and a lot of excitons have been separated. So the exciton separation in these films is quite efficient, and with a little built-in field even more, and it's also very fast. Now, how does this work? And for that purpose, we had a very enjoyable collaboration with Frank Ortmann's group in Munich. The oligothiophene are known to lay flat on the surface. So they have a very good pi-pi coupling in the transport direction. What Frank did was they did a tight binding Hamiltonian and made a supercell of 36,000 molecules. And the key parameter they introduced was some disorder in the way that you have a lateral shifts of the molecules. And there's an interesting behavior of the couplings. So here you see the couplings of the LUMO, the HOMO, and the molecular exciton. And especially interesting is that the LUMO and the HOMO both have a wild dependence on the coupling integral on the molecular shift. If you have the crystal packing, actually the LUMO and HOMO coupling are fairly small. But if you move a little bit the molecule to one side, you dramatically increase, for instance, the LUMO coupling here, or also the HOMO coupling. And therefore, by these shifts, you make the coupling of the transport states larger. And that, as Frank's group has shown, has now a very large influence on the system. First of all, they calculated here the absorption spectrum by a density of states of the molecular exciton. And when you compare the experiment, which is the dotted line with different calculations, you can derive the degree of disorder. They made 3 cases: weak L1, medium L2, strong L3. And here you get the by far nicest fit with the medium disorder. And the idea is now that this disorder increases, as shown on the previous slide, the coupling. And when you have an exciton and a molecular exciton state due to the coupling to the next molecule, you are generating a delocalized molecular exciton. And obviously, this delocalized molecular exciton can be separated in a fairly small field with the thermal energy. And therefore, that's the explanation, the disorder is, which makes this separation possible. And that rang a bell because years before we had studied ground state charge transfer or doping. And at that time, Max Tietze looked at the activation energy of doped systems, here phthalocyanines and a hole transporter. And the big surprise was that the activation energy, which should be limited by the Köhler energy of the bound donor acceptor pair, was actually extremely small, much smaller than any estimate of the Köhler energy, and even in the range well below KT. And the explanation we found was at that time with a calculation from Karin Sawyer and Markus Krammer.
And it's a very simple effect. If you have a disordered HOMO and a disordered dopant, and you reach a big enough disorder, you have an overlap of the states. And the calculation shows that you need between 50 to 100 MeV of disorder for both the host state and the dopant state, and then the temperature activation even disappears completely. So doping works because of disorder. In your mobile phone, you look at every day, the doping works because of disorder. And the same is when you generate excited state charge carriers, free charge carriers. So that's an important point. Now, for a novel phototransistor, I will show these results from Jonas Schröder and Johannes Ben-Dun. It's a device we published some years ago, organic permeable base transistor, where you control the electron flow with an aluminum contact, and the aluminum contact is actually a grating which is covered by oxide. And we noted by chance more that this device is very photosensitive. When you illuminate it, it shows a significant threshold shift. The effect is that you generate charge carriers, electrons and holes. The electrons go out, but the charge carriers are trapped at this oxide on the base. And this shifts, obviously, the potential of the base and therefore the transfer curve. And you get, by illumination here, a shift of several volts of the transfer curve. And the point is now that these charges stay for days on the base, and you get a very sensitive low light detector. And without going into much detail, Jonas could show that in terms of responsivity and specific detectivity, this was an excellent photodetector and about the best phototransistor, organic phototransistor ever made. So with this new device principle, which we'll still develop and adapt to different wavelengths, we also have another way without a heterojunction to generate an efficient photodetector. Here it is actually charge generation under large fields in C60, which works. Okay, now I take the liberty for a very few minutes. Oh, yeah, one more slide I forgot. Actually, now I'm happy to say that organic photodetectors are also in commercial application. This is actually a spectrometer. Each of these crossings here is one detector at a different wavelengths, and they are used for harvesting in a collaboration with Zeiss and John Deere. So after the solar cells, also photodetectors are now doing useful things. But I want to spend the last few minutes on a new hobby, and that is breaking this barrier. You know, when you talk about organic electronics, you are very close to our body because our body is also soft. It's water-based and does neuromorphic calculations, and it's very different from silicon. And in the past few years, we have tried to make electronic devices which are body compatible, and actually in the most radical way that you can implant them in the body and the body is resorbing them. And there's a good medical reason for that. Unfortunately, many of us will sooner or later in their life have some surgery where a so-called anastomosis is made. That means you need to cut out something of your intestine or whatever and later on connect it. And if this is leaking, actually you have a very big problem, and lots of people die because of such leakage of anastomosis. And it's hard to detect. And we had an extremely simple idea, which was the following. We put an organic electronic device at the connection point, and this device actually measures whether there's a leakage for about a week, then it's fine, and then the body resorbs it. Now the next slides show some intestines and blood. If you can see that, don't look at it. This is the device here. This is such a ring, and when you make this connection, which is nowadays made with a mechanical tool with titanium staples, we simply staple the device in the connection. And there now we do impedance measurements. The device here is shown after 2 weeks in a pig, and you see the body has completely overgrown it already. There's no inflammation, so it will be gone soon. But the key point is when we stimulate it, a leaky point by creating ischemia, we could measure electrically. This was a point when the ischemia was stimulated by breaking the blood flow. We could electrically measure the leakage very nicely.
And therefore, we have a new way to do that, and hopefully in a couple of years, such a ring will be routinely put into the connection point when you have it. And we can also actually do data analysis on this device, and for that we use organics. We use such polymer fibers as for reservoir computing, and you can do nice things. In this case, we measured electrocardiograms with extremely low power recently with nanowatts of power. So organic electronics can do more than solar cells and photodetectors. With that, my conclusions, I skip over that, and I thank the many people who did the work, and I thank you for listening.
Thank you very much, Carl. Other questions? No questions?
I think we're still digesting the images.
You don't need to think about the images. There was other parts of the talk. Anything? No? Nothing at all. And I have to say thank you again, Paul,
Pleasure.
for this nice presentation.